cherishing what you believe, and we will make it last. Not often we can see the beauty in the pain. Not often we can see the value that we gave. Now listen, little one, the walls will heal in time. No, it wastes time, but baby, you'll be fine. You'll be fine, fine, fine. Your skin, the touch of your hand makes me tremble within. The smell of your hair, but I here in my bed. Ever gonna be alone? 'Cause with you, finally coming home. I wanna be with you always. 'Cause that is what my heart says. That's what my heart says. I wanna be with you always. You are my world in every place. It's the things I can do. It's the smile on your face. And it's time to fly. I want to be in a better place. In a better place. Without your love, out of place. And without you, I am just a trace. I love you with all of my heart. Together forever, never to part. I wanna be with you always. 'Cause that is what my heart says. That's what my heart says. I wanna be with you always. Always, yeah. You are my world in every place. Oh, it's something to do, baby. It's a smile on your face. Smile on your face. And it's time to 나는 진짜 나빠 하나든 지켜지나도 나를 기뻐 그래서 너가 나를 살려 줬으면 좋겠어 네가 말까지도 책임질 수 있어 너 아직도 그렇게 행동하려는데 난 가지고 그렇게 행동하려는데 너가 말한 모든 나쁜 남자보다 내가 너를 많이 아끼고 있단 말이야 너의 맘은 다치 닮아간단 말이야 너가 싫어하는 나쁜 놈의 것들이라 너의 생각 절대 멈출 수가 없단 말야 너의 모든 걸 느끼고 싶어 Baby I love it girl yeah. 내 모든 걸 원하는 세상에 없어 너의 맘속에 가긴 어려워 너무 어려워 너의 몇 번째 왠지 몰라 너의 첫 번째 내가 떠올라 너가 처음 느껴보는 것도 싹다 Love it I go love it me yeah 첫 번째지 지나왔던 모든 것은 나의 덕이지 하지만 그 마음을 느껴본 적이 없을 거야 진짜 알고 진심이라고 이해할 수 있다고 남겨진다고
이 새끼는 나도 내게 빠져 너 친구들도 많고 나는 그냥 젖어 너의 전 남친은 진짜 삐까 번쩍하고 멋진 것도 많이 해봤겠지 나는 네가 처음이라고 이런 감동 알아 차라리 못 느껴봤을 싶어 너더라면 그 열등감을 느끼겠지 같은 맘이라면 그래 이게 첫사랑인 좀 더 아득할걸 근데 너는 많은 경험해왔잖아도 그게 존나 싫어 나는 어디 널 바라보고 있는데 네 오늘 널 다른 사람 몸속에서 얘기했어 너가 다른 사람 만나는 게 싫어 그렇게만 그것도 포함해서 싫어
Start. Okay, good morning, everyone. My name is Yusri Azzam. I am from Egypt, and I am the chairing of the focus meeting one. Actually, this focus meeting started with the intention of our Egyptian astronomy community to build a new telescope, which is expected to be 6.5 meters. And then we broadened our vision to include all existing astronomical observatories in Africa, and also the future observatories in Africa. And also we intended to include the dark sky and protecting the existing observatories in all Africa, and also the networking of all existing African telescopes. Then we have a broad vision to include the searching for new sites for observatories in Africa. We will start our. We are sorry for the last minute change of our program due to one of our colleagues who was unable to come today for his lecture this morning, and then we swapped his talk with Mariana. So Mariana will start her talk first. So I know everyone knows Mariana Bovic. She is Serbian Spanish astrophysics worldwide as professor of the Space Science and Geospatial Institute in Ethiopia, and her main research interests are galaxy information and evolution. In addition, over 15 years, she worked on development in astronomy, science, and education in different parts of Africa, and she received several awards and recognitions for her scientific achievements and contribution to society, particularly for her work in Africa. She believes that through education, science, and technology, we can combat to poverty in the long term and make our world a better place for everyone, regardless of where the children are born. So we are start now with Mariana in her talk.
I used to sit while giving a talk. Oh. So in the meantime, good morning, everyone. It's really great to see you everyone here, and managing to find a place because it was not easy at all. So I think it's a good sign, and let us see if I've been based full time in Ethiopia for the last 8 years. So the talk that I will be giving, it's a bit the summary of the current status of. No, that's not the one. Yeah, so it's about the current status of astronomy very briefly, and then how we can actually use astronomy and through the development of optical telescopes as well, which is the main point of this session for contributing to achieve the sustainable development goals. So shall I wait or shall I start? It starts with FM_, yes? Okay. Okay, great, yes. Where do I change the slides? I don't have anything. Okay. Here. Okay, great. And this is back. Okay, perfect. Okay, good. So my talk was scheduled for tomorrow, so I will try to fulfill with expectations of 20 minutes, but I was actually preparing myself for tomorrow for the talk. Yes, so this is a bit the content, as I said already. So I will start with a brief introduction and summary about astronomy in Africa. When I started my PhD 20 years ago, I had clear that after my PhD, I want to work in Africa, and that's what I did. I moved to South Africa, and at that time, South Africa was the only country where I was able to get a job as a professional astronomer. Nowadays, that picture is very, very different. As I mentioned previously, for the past 8 years, I've been fully working in Ethiopia, and then there are many other countries that currently are doing, is this? Yes, that currently are working on the development of professional astronomy. In this map here, you can see just in terms of the infrastructure development, what is the current status. So those observatories that are already there, others that are on the way to come. And on the left, you can see the map that even when we come to other aspects of astronomy, like just outreach, education, and how much the general public is interested about it, currently there are more than 70 astronomical amateur societies across Africa. So and there the number is growing all the time. So there has been really an amazing progress in terms of astronomy development. In this paper here, a few years ago, we made a summary of the development of astronomy and space science, and we will be coming soon with the update of that as well. So when we now look that map into how it actually, the infrastructure is distributed in terms of radio astronomy, gamma ray or high energy astronomy, and then optical telescopes, well, this is what you can see. So with the SKA and then the ABN, these are the countries that are participating in the development of radio astronomy. Few countries like Tanzania, Namibia, starting also the development in millimeter regime, and the idea to join the Event Horizon Telescope. The HESS is there, and also both Namibia and South Africa are taking the strong participation in the CTA. The coming next generation gamma ray telescope. And then in optical, you can see a bit how the observatories are distributed. So now I will speak a bit more, taking into account the main topic of this focus meeting. I will focus a bit more on the optical telescope. So I will not speak about radio astronomy, neither high energy. So when we come to the optical, there are several countries, as once again, you can see in this map. So over the last 10 years, Morocco was really, I would say, besides South Africa, the country that made the most significant developments. You can see here the Okamden Observatory with several telescopes that are there in collaboration with different countries. That includes also the TRAPPIST-Nord telescope that is focused on observing the small bodies, but also doing the study in stellar astronomy. And they are in particular, particularly active in different collaborations related with extrasolar planets. Algeria, well, the very old observatory is still there, but because of the light pollution in Algiers and the lack of maintenance as well, now it is only used for like outreach education, but not professional astronomy. But there are plans currently there is a site testing going on with the plans to put another observatory in collaboration with European Virgo. So that will be more focused on the detection of gravitational waves. Egypt also made significant developments. The Kotami Observatory is there with almost 2-meter telescope that that is still working, including spectroscopy. But because of the light pollution, so please see us. Yosri will be speaking more about that, and Zuhair tomorrow about the Okeimden Observatory. So currently the site testing is going on with idea to put a bigger telescope, the Egyptian Large Optical Telescope, that probably will be around 6 meters. Here you can see the small Entoto Observatory with 2 telescopes. Both telescopes are twin telescopes, 1 meter. And this is about 10 kilometers from Addis, with the possibilities to do both photometry and high resolution spectroscopy, but with many, many challenges. I will not have time to speak more about it, but you will see through the talk actually more about the activities that have been carried out. About 10 years ago, Burkina Faso also came up in collaboration with colleagues from South Africa, came with the idea to establish a small observatory. So a small 1 meter telescope has been, that you can see here, has been moved from Chile to Burkina Faso. Then the construction of the dome started, but unfortunately due to the political instability and the conflict that is affecting the area where the observatory was planned, it is a bit in the standby phase. Kenya also made improvements, going currently through the site testing with the idea to put a small observatory in collaboration with the UK. And then I will not speak much about South Africa. I will mention it, the SAAO, a bit later through different examples. But here you can see a number of telescopes, including SALT at the SAAO, and then one of the most recent, the small optical telescope that is working simultaneously with Meerkat in radio. This is the project that we are currently starting across Africa. So David will be speaking more about it tomorrow morning. So the idea of this project is so basically here you can see the currently available telescopes and observatories in optical, and the idea is to come up with this African integrated observation system that will connect all of the telescopes, make them robotic as well, and make them working as one system. So currently that work is going on at the SAAO. So the idea is that once, including SALT, the idea is that once the knowledge skills are there, that is then transferred to the other countries, Morocco, Egypt, Algeria, and Ethiopia, so that we can actually strengthen collaborations, research projects as well, and the use of small telescopes as well. So this is the map where we can see currently the largest telescopes between 4 and 11 meters. And you can see that we know the places where there is accumulation of these telescopes, like Hawaii, Chile, Canary Islands. And when we consider the whole African continent, we only have one telescope that is in this range, that is above 4 meters. And that's the SALT telescope, 11 meter aperture. On the other side, if we look how the light pollution is, we can see that the African continent actually has still dark skies as one of the natural resources, and therefore a huge potential for the development of observational astronomy. So definitely beside South Africa, there is a huge potential, in particular in Eastern Africa, where we have high mountains, many mountains above 3,000 meters, many of them that are very dry as well along the year. So there is definitely a lot of potential there. So that is a bit the current status when we consider the infrastructure development, as I mentioned at the beginning. But when we come to the development of astronomy in other aspects, like human capacity development, institutional development, opening of space agencies, site testing, and so on, this is a bit the map that we currently have, where we can see that actually the majority of African countries are currently having some aspects of the development of professional astronomy. So at least in terms of training people, giving postgraduate courses and so on. So recently we did this survey, Astronomy in Africa survey, under the Science Committee of the African Astronomical Society. So you can see a bit what was what were the countries that contributed to the survey. So we got 60 feedbacks from 18 countries, but the feedbacks that we got is from people who are actually leading the astronomy development in their countries. So which means that they really know what is the status. So I will just briefly summarize, because the feedback that we got is really important. It is really reflecting a bit the current status, but also the challenges that are there that I would like a bit to share with you, because I think they are important. And this picture is a bit, it's in terms of these are not exact numbers, so it doesn't include the whole community that is there doing professional astronomy on the continent, but it does represent a bit what are the principal fields that people are interested about across the continent. So we can see that those fields that are more present in terms of the research is cosmology, galactic extragalactic astronomy, stellar astronomy. Then, of course, data and methods plus instruments, because, I mean, we are all using that. But what is also very interesting to see is this last part, where the majority of people shown interest that they are actually very much passionate about using astronomy for development, you know. And this is something that was really a very important aspect of all the collaborations that we had across the continent over the last 15 years, no? So when basically, I mean, all that we've seen now, except South Africa, most of that development came in the last 10 years, which is really remarkable, no? So let me first just summarize a bit the signs of that amazing growth in Africa over the last 10 years. So many new postgraduate programs. So basically half of the continent currently do have programs in master and PhD in astronomy. I here put only some of the countries. Then strong increment in the number of professional astronomers and therefore research. So for example, this is actually not even in 10 years, this is even less. In 5-6 years, we are now having 3 times. So the growth in research papers is really exponential. The significant infrastructure development, as you could see, strong institutional development. So many countries, about a third of the countries now do have like research centers or dedicated departments for astronomy research. Establishment of the AFAS was also very significant in 2019, a re-establishment in 2019. And now AFAS really became, in a certain way, very active, dynamic society, and in a certain way, the voice of the African astronomy. The public awareness outreach increased everywhere, and also the political engagement, you know, which is something that is very relevant, because if we don't have the attention of the policy decision makers, we cannot do science, no? So definitely there is more funding there as well, and South Africa is really playing a very important role, and South African government, in actually promoting the awareness among other governments on the continent. The list of the challenges is much longer, so I will dedicate also some time to share with you the challenges that the colleagues raised. So the first thing is that all the development has been really remarkable, amazing in the last 10 years. Please keep in mind that most of the countries are really starting from scratch. So in Ethiopia, for example, when we started 8-10 years ago, I mean, you start from scratch with everything. So Solomon will be giving the talk tomorrow. So please, he will speak more about different challenges that are there. But when you start from scratch with a very small number of people, because this is another point, very, very limited human resources and a very small number of qualified people. So currently we have many students that do want to do their master, their PhD, they're motivated, but then very small number of people who are qualified so that they can do all the courses, supervision, and so on, and then everything else, no? Then lack of supportive infrastructure for scientific development. When previously, before Ethiopia, I was in Spain, I was just coming to my institute, doing my research. I didn't even think about what everything is needed there to be done so that I can come and do my research. No? And then when I came to Ethiopia, I realized that actually doing a research, you need so many levels, no? There are so many people going from administration and everything else. And when you don't have that system, then it's on you to do all of many of these points. No? So you convert yourself in absolutely in everything, you know. So this lack of supportive infrastructure, bureaucracy, administration, and so on is really taking a lot of efforts, time, energy, and so on. Lack of funding, definitely, and then support from the local government. So since the field is still quite new, there is a lot of work to be done to constantly convince policy decision makers why actually it is important to do what we are doing and what we want to do in terms of astronomy, space science, and so on. This is another very important point, that astronomy in Africa is still not accessible to all countries, as we could see. Work overload, including teaching, lack of the time for research. This is a serious problem because of what I said previously, that the number of qualified people is very small. So then you have a lot of duties on your back. A lack of funding to contract actually MSc PhD students, postdocs, or to establish the research group and then the facilities, including computers. So actually still many colleagues and students are suffering with even getting the access to the basic infrastructure, you know. So just basic infrastructure, such basic as computers and external disks. Then attracting new students, this is also challenging because again, the funding is not there. Uncertainty due to the non-permanent position. This is not only for Africa, it's a global problem that we have. The administration, again, related with what I said previously, the limited telescope time, and actually the number of proposals coming from Africa is still very, very low. So this is something that we really have to improve in the future. Mobility is a big problem, again, due to the lack of information, lack of funding, lack of international collaborations as well. Very often living far, low salaries, very big problems. So this affects then the brain drain as well, especially for the young researchers. Now we are left with only one journal, Astronomy and Astrophysics, where, and not all African countries, where we can actually send our papers for publishing. But if astronomy, astrophysics change the policy, we will be forced to actually publish in lower quality journals, even if we have the first class science done, just because the publishing rates are very high. And this is the real problem that we are having across the continent. This is still something to be worked on very much, promoting, I mean, sharing the awareness with policy decision makers about the importance of astronomy, and very, very important point, the political instability and conflicts that a significant number of countries are going through, and that definitely is affecting our work. So I would say that, to go over these challenges, really a key is to work together. This was the key over the last 10, 15 years across the continent. There is really an amazing community and connection between all of us, because we are all in the same boat. When you go from one African country to another, South Africa really played a strong role. I think I will have to speed up. A strong role in promoting astronomy among other countries. So this is definitely something that we have to focus more on. So now the second part is coming, and I think I'm left with only a few minutes. So basically, astronomy is really contributing in the shorter or longer term to all sustainable development goals. So I will, to in line with that, now we have also the African Union that is actually having more awareness about it. So there have been in the last few years several improvements, the establishment of the African Space Agency, the first space strategy, where astronomy was highlighted as one of the important fields. We also shall not forget that astronomy is in the heart of all the digital revolution in which we are currently, with the Wi-Fi, different components related with computing, communication, GPS system, positioning, navigation, and so on, that we cannot really imagine our life without. But then when we come to the big data, new technologies that are at the heart of the IA revolution, well, the SKA is going to play really an important role, and that will place basically African continent also in the center of these developments. So I would say that the exciting times are really coming. let us also remind us that one of the for me, maybe even one of the most important aspects of astronomy and its contribution to the development, social, economical, environmental, is the knowledge generation, because we are talking about cutting-edge science that constantly is bringing us as a humankind on the border of our knowledge, and therefore contributing to the development of, to all the knowledge generation, technological development as well, and to what is the contribution to the knowledge-based economy from the resource-based economy. And this is something that is really important. We all know that African continent has been there for centuries, used for simply prime materials and as the continent for the exploitation, resources, the human exploitation as well. And this is something that really has to change. So bringing Africa more in the context of knowledge generation, contributing to the science development, technology development, and innovation is really a key. And I will just give now a few examples. The very strong contribution to the quality education. Here you can see some of our very first MSc PhD students that we started training in Ethiopia, but East Africa as well. Most of them, or basically all PhD students, most of MSc students, they are already lecturers at some of the public universities. So when they finish their studies, they go back training hundreds of other students. So basically we can really, by bringing strong skills to the students, we can actually improve the quality of education in Ethiopia and East Africa. And this is something that we can really already see the strong results. Having astronomy development, I'm sure that all of us who are here and participated in education outreach, you know what I'm talking about when I'm saying that astronomy is really a powerful tool for promoting science education and inspiring kids and the global community as well. So here you can see in Ethiopia the long queue every time we go to the schools, villages, especially when you go to the more remote, more rural areas, more challenging conditions, you will get more kids being really inspired, So you can see always these long queues and the motivation of the kids to look through the telescope. Here you can see the students. So basically before the war in Ethiopia started, the conflicts in 2020, we had every year more than 10,000 students coming to visit Entoto Observatory. It's the only observatory that we have in the country. And currently in all East Africa, and students would travel 2-3 days in order to reach actually the site. So very big motivation that is there. Another example is the contribution to the economic growth, so the SDG 8. Through the bringing the qualified the skills and highly qualified people that then can work in different sectors. This is the batch of some of the very first students that we trained that currently are working all over the country. And here you can see some of the people, the training that was done in last year in training the tourist guides in astrotourism. So these are just some of the examples. I think it's clear the contribution of astronomy to the technology development. We have the great example of SKA in radio. We can see all the innovation that is coming with EELT, with James Webb as well. So we really have to put more emphasis on development of optical astronomy on the continent. In particular, considering that the dark skies are there, that this is still one of the natural resources. There have been already improvements. So Morocco, South Africa, that already have protected areas. We are now working under the African Astronomical Society on the development of the very first African dark sky strategy. Last year, we hosted this symposium on the dark skies that was happening in Ethiopia. I will not have time to speak about the collaborations, but I would like to stress about this, that we also can use the optical astronomy, telescopes, astronomy in general for really promoting peace. And I think nowadays we really living in the world that is so much polarized more than ever in the last 100 years, we shall promote this message. You can see here some of the activities that have been carried out in Ethiopia, in the northern area, in Nigeria by our colleagues, Olainka and others, and then by Jamal in Mali. But there are many other activities going on. We will have on Friday the session about astronomy in conflict zones under Division C, so please come. And I don't know, do I still have 1 minute or not? 1 minute. 1 minute, okay, thank you. So I will finalize with this. So basically this is a bit the summary, just using as an example the South African Astronomical Observatory, which is really a bit the role model that we have on the continent, inspiring many other countries. I mean, we are all aware about the number of observatories that are there, many of them not being South African, but South Africa did a great job in attracting different partners, different countries that put their telescopes on the South African land. And I mean, here is just, here are only some of the benefits, no? That due to this, I mean, that brought the development of the South African astronomy and science, bringing very strong international collaborations, the strong technological development that now we have people that are capable at home to produce and build new instruments like the new IFU instruments that the SALT is now hosting, the employment that is generated through the observatory, the protection of dark skies, that due to this, the big part of the Kuru Desert has been protected. That opened the path definitely to all the governmental support, seeing that, you know, that South Africa can attract all the partners. And definitely this observatory played a crucial role in also opening the path to other aspects of the astronomy, such as the radio astronomy, no? That you will hear a lot about it during this symposium. And basically, when we combine all of this, we also come to the strong contribution to the social economical growth of the country. You know? So this is a bit the inspiration really for other countries as well. So to summarize, if we include all the previous, then really in the long term, we can contribute to reducing inequalities among the countries, and then also combating poverty in different forms if we really make the Africa stronger through the education, science, and technology. So I would say that really it's the time for Africa, and to always keep in mind that, you know, that when we speak about investing in astronomy, investing in science, it's really not a question of luxury. It's basically a fundamental need if we want to see the world being more equal, more fair for everyone, you know? And I'm sure that, you know, that all of you who are working on astronomy development in Africa, you are getting the same question constantly, why there is astronomy in Ethiopia or Nigeria or Kenya or Burkina Faso, when there are many other challenges. No? So keeping this in mind, it's really important. Thank you.
So we have a few minutes for questions. Please go on.
Thank you for the book. It was very cool and inspiring. I wonder, how do you manage to retain all the students that have been trained in Ethiopia already and stuff, or rather advise them not to leave the country and help Ethiopia get better? Because in other countries, you see a lot of them, they get their education and leave.
Yes.
So how do you ensure that they stay? How do you ensure that they stay in Ethiopia?
Yes. So the crucial point there is that they do have secured the job positions. It's a key point. It's not sufficient, it's not enough, but it's really the key point. So as I said, all of our PhD students are already lecturers at some of the public universities. So basically, the Ministry of Education wants to, it's a bit like in Europe, some time ago, or in other countries where now universities only have PhD holders, but it was not like there all the time. So now we are in the phase that people who are at the universities, they have to, many of them just have the undergrad, the bachelor, the undergrad studies, And because there are many new universities that have been opened across the country in the last, when I went first time to Ethiopia in 2015, there was a bit more than 20 universities, public universities. Now there are more than 50 public universities. So the number doubled in 9 years, no? And you don't have PhD holders that are there. So that's the key. So basically the program that Ethiopia has is that they are giving their training, giving the PhD to their lecturers, staff members. They do it basically by getting the study leave, receiving their salary during the study time, and then they have commitment when they go back to teach at the university for a double amount of years. So if their study is 4 years, they have to teach for another 8 years. If in that time they want to do a postdoc, very often they can do it, then coming back and so on. So it's really a system that is quite efficient. It's not perfect, of course, and there are other aspects. I mean, the political stability is very important. So now there is a problem that people want to leave and so on, but it's quite efficient system. Yeah.
Okay, thank you very much.
You're welcome.
Other questions? Okay.
Thank you very much. I'm James Lowenthal from the United States. I am here with colleagues Federico Di Bruno and Connie Walker and others from various parts of IAU that are focused on site protection and protection of the night sky. Thank you so much for this inspiring talk and for highlighting the many challenges, including the erosion of the night sky from light pollution, which is a challenge that astronomers around the world share. We may not share the political or other unrest or other challenges that you've highlighted, but we all share that problem. I invite you to come to the session tomorrow on the Center for the Protection of the Dark and Quiet Sky, to the business meeting for our Commission on Site Protection, and to the Executive Committee Working Group 6 meeting about dark and quiet sky protection. And I wonder if you have any, so those are tomorrow and next Monday and next Thursday. And I wonder if you have any words, additional words to say about the challenges faced specifically in Africa, or maybe more specifically in Ethiopia, about protection of the night sky, specifically from ground-based light pollution, but also thinking about the new problem of the satellites.
Yes. Well, in case of Ethiopia in particular, maybe Solomon would like to say a few words as well. Well, the dark skies are actually, I mean, in Ethiopia, still about 60% of the population, actually more than 60% of the population doesn't have the access to the electricity. So on the other side, it's the second most populous country on the continent after Nigeria. So there are more than 120 million people now, no? Which means that the dark skies are there, but there is, because many people don't have the access to the electricity. So the protection of dark skies is facing several difficulties. One is definitely still the lack of awareness. The lack of awareness among the policy decision makers. Other problems are the population that is actually spread everywhere. So even when you go to the high mountains above 3,000 meters, you still find many people living in the highlands. No, so then protecting the areas without having to forcibly displace people is not a solution. You know, is not an easy task to deal with, you know. But even so, there are areas, I mean, there are national parks that are already there that could be used, you know, for, you know, adding additional protections so that some scientific development can be carried out as well. But yeah, I mean, the lack of awareness, the population, distribution of the population as well, the lack of infrastructure is a big problem as well, because and all the demography of the country and I mean the geography, because you have a very complex systems of mountains across the country. So that's another difficulty. Funding is another difficulty as well. And then the very important problem is also how the land is managed, you know. So getting permissions for, like, you know, protecting certain area And you know, there are many other aspects that are playing a role. No, the land distribution, ethnic groups who are possessing the land, how that is regulated with the government. So the land issues are big issues in Ethiopia, no, and other parts of Africa as well, no. So I think that, I mean, the first thing we should start with is really awareness, because there is no really sufficient awareness. I hope that the strategy that I mentioned that is just in initial phase, basically still as an idea under the African Astronomical Society, to come up with a strategy regarding the protection of dark skies that might help. South Africa now has that strategy, and also for the astrotourism as well. So that's a good guidance. I mean, it's a good guide again to have for the other countries. And yeah, that's a bit the summary. I don't know if Solomon, you want to add anything. Yeah.
Okay.
Thank you very much, Mariana, and Lily, your nice presentation to highlight all the development of astronomy and the challenges in Africa. In particularly to Ethiopian case, especially to dark sky, of course, the majority of the Ethiopian people living in the countryside, and 75 to 80 people percent of the Ethiopian people living there. But the most important one is, as she said, is awareness. And at the same time, there are some important places that already preserved, not only for space, but particularly relating to the national park. Those national parks are highlands and more nearly to important for astronomy research and also for other activities. Then I think in order to proceed to the light, to the dark skies, my recommendation is, of course, we have already planned to work to the awareness of the community and also continuously to engagement and relating to those community with some tourism that can be able to use. If the community are using some sources or small tourisms that will not be affect the astronomy, then it will be possible to protect the light sky. And the last one is now real to creating very strong awareness with the policymakers. Our space policy clearly indicates that how the astronomical sites are going to be preserved in the policy. That policy was approved by the government 2018, but still needs to be more policymakers awareness. Then the most important is that is a very important thing, and also long time preserving the site and selecting maybe the most one. Thank you very much.
Okay, thank you very much. Maybe you have more discussions on Slack, or you can meet Mariana or other people at the break. So because we are out of time, and we have to continue our session by the second talk by Rosalind Skilton. Is here. So her talk has a title of an overview of the South African Astronomical Observatory telescopes. Please go on.
Thank you. Can you hear me? Good morning, everyone. I'm Dr. Rosalind Skelton. I'm currently the Acting Managing Director of the South African Astronomical Observatory. And after that lovely overview of African astronomy, I'm going to zoom in on what's been happening in South Africa, which is the most established observatory on the continent. So the South African Astronomical Observatory is one of the national facilities of the National Research Foundation of South Africa, which is also the host of this meeting. So I'm sure you'll see a lot about the NRF over the course of the next 2 weeks. Our aim is to explore the universe and to share what we do with society, so to make that exploration for the benefit of all society. It doesn't seem to be moving. There we go. So South Africa, the South African Astronomical Observatory is the home of optical and near-infrared astronomy in South Africa. We have a long history dating back to the 1820s when the Royal Observatory was set up at the Cape of Good Hope. What we do is provide telescopes to the astronomical community in South Africa and worldwide. We do the research at SAAO as well, and we are very involved in teaching and developing the next generation of astronomers and engineers, building new instruments and working on the technologies related to astronomy, and also sharing that science with the world. We have 2 sites with about 130 staff split over the 2 sites. And here in this map of the world at night, you can see why we had to move away from the urban area of Cape Town. So in about the 1960s, it was realized already that the light from Cape Town is just becoming too much. And sites were explored around the country, with eventually being settled on Sutherland. So you can see from this map that Sutherland is still a very dark site. It's a superb site for astronomy and still one of the darkest observatories in the world. And this map just orientates you to show you also where the Meerkat radio telescope is further north in the Northern Cape. So Sutherland is in a very dry region known as the Karoo, a semi-arid region. And Ramatola Sefako will talk more about how we've maintained that dark sky. So there are certainly challenges. It's an ongoing effort to keep the skies dark there. But as you can see from the map, Sutherland is very dark. Our research at SAAO focuses on a few different areas: transient astronomy and stellar evolution, galaxy formation and evolution, exoplanets, and more relatively recently, exoplanets and planetary science, looking at asteroids. We have multiple telescopes, as you'll see from the rest of this presentation, and you saw already in Muyana's talk. So we maintain and operate those telescopes, and we have engineering laboratories and a very high precision workshop that we're very proud of, where we build instruments ourselves. We have a fiber laboratory where we are working on astrophotonics and developing a new IFU for SALT, and we'll continue with fiber astronomy development, and this very high precision machining shop. We also have been involved in training. So the National Astrophysics and Space Science program was largely driven by the SAAO, and it's now more than 20 years old. So we have a strong history in training students in postgraduate astronomy. And we also have people coming through the engineering fields at SAAO. And we have a very strong outreach and education department that shares astronomy with learners and educators across the country and does a number of public events. I'd like to invite you all to visit the SAAO during your time here in Cape Town if you haven't yet been there. So we have visits to both our sites over the course of the GA. There are daily tours at SAAO in Cape Town, where you can see our historic building and our old McLean telescope at 10 o'clock and 2 o'clock, and stargazing, and if the weather cooperates, and an open night talk every night. And then you can visit Sutherland this weekend and next weekend as well. And I really encourage you to visit our website if you'd like to find out more details about that. So if you do go to Sutherland, and I highly recommend stopping by there if you can, we have the beautiful dark skies, and you'll see multiple telescopes up on our plateau. So this image is already a little bit out of date. We have the new Prime telescope, which isn't shown here, and there are about 30 different facilities on the plateau now, including some smaller experiments that aren't necessarily for astronomy, but most of them being our astronomical telescopes. In the background there, you can see the SALT telescope, the Southern African Large Telescope. Then there's our 1.9 meter, which is the next biggest one on the right-hand side of the image there. So this is the list of our telescopes. I don't expect you to read through them all, but I'll highlight a few. We have our flagship facility, SALT, which you'll hear about in Connie and Brian's talks later in this meeting as well. Then we have 3 1-meter class telescopes that are the traditional SAAO telescopes. One of them is a new 1-meter telescope called Lesedi, which is fully robotic and can be operated autonomously. Another one that I'd like to highlight is the Meerlicht telescope, which tracks where the Meerkat radio telescope is pointing. And obviously that's very important for to give you simultaneous optical and radio astronomy data. And then we have partnerships with Japan, our IRSF telescope, which has been there for more than 20 years now, and the new Prime telescope, which is a 1.8 meter telescope. So a number of other partnerships and collaborations. Many of these enable the South African and international communities to apply for time, so they aren't limited to just those partners, but we host them on behalf of our international partners. And the last one that I'd like to highlight is the Atlas telescope. So this is a relatively new telescope that aims to detect asteroids and moving objects, transient objects. And in the last year, it detected about 46 asteroids and 5 comets, so doing an excellent job at that. SALT, as I mentioned, I won't go into a lot of detail because there are other talks that will focus on SALT, but this is our flagship facility, and it's the largest telescope in the Southern Hemisphere. It has, in addition to the South African National Research Foundation, it has 7 other international partners. And South Africa contributes about 50% of the operating costs of SALT. And that means that we have about half the time on SALT available to the South African community, but more broadly, the African community. And we really encourage collaborations with the South African astronomers. We have some exciting developments on SALT recently. So in addition to its workhorse instruments that have been there since it started full science operations in 2011, and another one added in 2014, we have now a near-infrared spectrograph, which was built by the University of Wisconsin. And this year we've added a slit mask integral field unit. So this is the first capability of its kind on the African continent, developed by Sabasatchi and our laboratory in Cape Town. So we have the capability now to do that kind of high precision fiber work here in Cape Town. So this is a very novel instrument that takes the light from many fibers and redirects that light into the slit. So it can be operated just like any other long slit on the spectrograph, relatively easy to operate and use, but it offers us that integral field unit capability. And then we're also very excited about the new laser frequency comb on the HRS, our high resolution Echelle spectrograph. So this will enable us to do high precision radial velocities that are required for exoplanet work. And we had first light on sky with this LFC in April, and we will continue to develop the software required to make those kind of observations routine in the next 6 months to a year. So the other SAAO telescopes are our 1.9 meter, which is affectionately known as Old Orange, the oldest telescope on the plateau. It's actually was built in the 1930s, but it's been continually updated and improved, and now can be completely remotely operated. It has a low resolution spectrograph, a high speed polarimeter, and some high speed imaging capabilities. Then there's the modern 1 meter telescope Lesedi, which has an instrument called Mokodi, the low resolution imaging spectrograph, and a wide field imager called Sibunise that's still being commissioned. And we have our older 1 meter telescope, which also has high speed imaging. And from next year, we'll have a polarimeter called Wallop, which is a collaboration with India. So rather than decommission older small telescopes, we decided a few years ago to really focus on this project to combine and make the best use of all of our telescopes together. So we've called this the Intelligent Observatory Project, and it aims to network the telescopes to make them fully robotic and remotely operable, to enable new ways of scheduling observations so that you don't have to stick to the traditional sort of 1 week blocks where an observer has to go up to Sutherland and be there at the telescope in person. And we've already made excellent progress on this. So the SAAO telescopes are now remotely operable. The Lesedi telescope can be fully autonomously operated with interrupts from if there are transient alerts going off from other telescopes around the world, that can interrupt the queue to schedule specific observations of those transients. And there's now a lot more work to be done to work particularly on the software side to make this more intelligent, to use artificial intelligence to develop the system. So our old orange telescope, although it's the oldest on the plateau, it's now can be, you can switch between instruments on the fly. And so a lot of work has been done to really develop and keep the older telescopes up to date. The next steps are also to include some of the other telescopes on the plateau, like PRIME and the IRSF and our other international partnerships, to help them make those telescopes robotic or remotely operable, at least, so they can be operated from Japan or elsewhere, and to bring the telescopes together with our observatory control system so that they can really be used as a network. And we're quite excited about new collaborations that are developing, for example, with the UK's Hartree Centre on artificial intelligence and using artificial intelligence to do this kind of networking and making better use of the data. So as we look into the future, we have a very exciting time ahead with the first dishes of the SKA already going up, and the Meerkat, one of the best, the best radio telescope in the world, but it doesn't operate in isolation. We need the optical counterparts and the multi-wavelength data to really make the best use of it and fully understand what we're seeing. With new surveys coming out like the LSST Rubin survey and all the other transient surveys that are going on, even with smaller telescopes, you really need to have follow-up capabilities. And so we've developed this whole suite of instruments. We will keep developing it that will enable this kind of automated, intelligent follow-up of interesting events going on around the world. Thank you very much.
Mike, please.
Hi, Richard Vaughan from the Kenya Optical Telescope Initiative. One constraint you have, of course, is your latitude. Given the developments in ICT and the potential for remote operation, would you see the possibility of collaborating actively with telescopes that are sited further north so that you have access to the northern celestial hemisphere?
Yes, I think that would be really fantastic. And I think David will talk also about the African Integrated Observatory and how we can expand that network to not just be an SAAO intelligent observatory, but an African observatory. So we have, the advantage of being the only telescopes at this longitude in the Southern Hemisphere, but it would be great to also have that latitude.
Any other questions?
Thank you very much for your nice talk. So I'm Michitoshi Joseph from NAOJ. So, and in Japan, we are facing a very difficulty about the keeping and the fostering the astronomical instrumentation stuff. So, and you said that you have a, how to say, the educational course in technology in SAAO. So, actually, many excellent students are going to outside from astronomy after graduation. So they go to the commercial industries because they have much salary. So, but how to deal with that kind of problem in SAO?
It's certainly a challenge that we face as well. And I would say the data science industries are absorbing quite a few of our astronomical students. But we have recently started a master's course in instrumentation in particular. And we're just trying to build up our expertise and offer training in instrumentation and in this these high-tech fields. I think we see it as benefiting the country anyway, if students will go into other areas of engineering, but we of course would like to keep some in astronomy. So it's a challenge worldwide.
Last question.
Jean-Baptiste Ikwaya from the Vatican Observatory. So, I mean, it's very nice actually what you are doing. But my question is how flexible you are to put out there your data so that, I mean, university who don't have telescope, they can actually use your data and do real science with that.
I think there's definitely an opportunity there. We are working on our data archives and making our data accessible. SALT already has a data archive that all the data that's no longer proprietary. And for most partners, it becomes open after 2 years. So all of that data is available, but we're working on all the other telescopes at SAO and making that data more accessible. So that's part of the Intelligent Observatory project.
Okay, thank you very much. So we will move now to the next talk by Encarni Romero Culminero, and her talk about Beyond the Borders, fostering collaboration and building capacity in African astronomy through SALT, South African Large Telescope. Okay.
Can everybody hear me? Is that better? Okay. Hi. Thank you very much for this opportunity to come and talk to you about my favorite telescope, about SALT. Thank you also to Miriana and to Ross to put everything into context. So that makes my job a lot easier since I have a lot less time to talk about my favorite telescope. I am Encarni Romero Colmenero. I'm the shiny new director of SALT, and I'm here to tell you a little bit about my telescope, but also about the efforts that we've been putting into making SALT available to the wider community in Africa as well. Nice. Coming? Sorry.
We are sorry about these technical problems because this is the first session and we are facing these problems. I think you can go to him and to try to find your presentation.
No. Do you need me to come again? Sorry about this. How do I go back?
Don't press.
Don't press. Okay. Okay. Yes. Cool. Does this work? Yes. Okay, sorry about this. Thank you for your patience in waiting for the technical problems. SALT is, as it was mentioned before, is the largest telescope in the Southern Hemisphere. It's a it's a 10-meter class telescope. It's also a private telescope. It's accessible to PIs in partner institutions, and there's a list of all the partners down there. But also, most importantly, it's also accessible through collaborations. Also to African PIs, and there's also opportunities to buy telescope time through, for example, through the ORP, and lately Carnegie Mellon University also bought some telescope time. And soon American PIs will also have access to SALT through the LSST program. There's also open access to all in the form of DDT. We have a few hours per semester available, and all you need to do is send an email through DDT and we'll guide you through a process. So it's quite simple. Where is SALT? The headquarters are actually in Cape Town, and as Ross says, please come and visit. They're also full of historical telescopes there. And the actual telescopes are in Sutherland. Why are they in? I'm not touching. Why in Sutherland? Mainly because of the dark skies. Ross also showed this image of how how dark the skies are in Sutherland. We're actually amongst the darkest skies in the world. It was recently published. We were about 4th or 5th darkest skies in the world. We also don't have strong seasonal weather impact. They're going by themselves. There's also not very strong seasonal weather impact. That means we're open all year round. And that is important when it comes to Q-scheduled observations. The telescope is fixed in altitude. The telescope. Are you guys playing with this too? Okay.
We've got auto, so turn it off.
Okay. With yeah. I'm just gonna start again, aren't I? Everyone's forgotten what I said already. Actually, this is it now. Technical problems. Arrows are hexagonal, so it kind of looks like the pupil that's led the telescope through. Well, less scattered light.
Yeah.
I can go, good. So I just wanted to point out to you, one thing is that the telescope is fixed in altitude, so we have to wait for objects to come into the visibility annulus, and we track them with a tracker right at the top that you can see over there. The instruments are sitting here at the top, and this tracker just basically tracks as the Earth rotates and tracks the objects through the sky. What are SAAO's specialties? It's a very large telescope, so the large collecting power is a no-brainer. The skies are mentioned as a very dark, although we have only modest seeing. And because it's fixed in altitude, it is fully Q-scheduled. It doesn't make sense to try and have guest modes where you would get an observing for a night. Instead, everybody puts their observations into it. And they're fully Q-scheduled by the team. What are we good at? Well, diffuse low surface brightness spectroscopy is one of the keys of things we're good at. Bright objects are also very observed very efficiently because they're quick to point, quick to identify. We can change instruments and observing modes while we're pointing, so everything is in season all the time. We also have blocks that can be submitted at any time, so we're actually very good with the TOOs, target of opportunities. We have rapid reactions, and we also have online some very rare modes on other telescopes that are available at any time, such as polarimetry, high-speed modes, and some rather mixed modes. So SALT is mainly, because of its Q-schedule nature, it's a spectroscopic survey telescope. It's most efficient with programs that are scattered with targets that are identified all over the sky. And also we're very good with TOOs, as I mentioned. What kind of instrumentation we have? We have an acquisition and science-grade camera. Our image field of view is about 8 arc minutes. It's actually aging, this camera, and we're looking into replacing it. So if anybody's got some ideas, please talk to us. Main workforce instrument for on good weather and dark moon is the Roberts-Dobbs spectrograph. Is basically an everything type instrument. It can do imaging, long still, multi-object spectroscopy, and as I'll tell you right now, it also can do IFU spectroscopy. Medium resolution are to about 10,000, and you can basically chop and change through gratings, filters, and grating angles. Also has high-speed imaging, high-speed spectroscopy, polarimetric and spectropolarimetric modes. The recent upgrade I mentioned earlier, Sabyasachi sitting over here. So this has been developed in-house. It's an IFU that fits in our slit mask magazine, so it's easy to chop and change. So again, same thing, everything gets done on the fly. And you can see how it would save observers a lot of time if instead of using lots of exposures through long slits, you just basically take 1 second exposure with the IFU. So this is already had first light, and it's completed engineering commissioning. Is being offered to all PIs on the next semester, starting in November on a shared risk basis. That's a picture there of what the IFU looks like. It's actually teeny tiny, so don't be deceived. The high resolution spectrum is also available at all times. It's in a shell with various modes and various different resolutions. And the high stability mode has the highest wavelength resolution, the accuracy to about 3 to 5 meters per second. We can either use our iodine cell or the simultaneous stereomargin for calibrations, which is crucial for exoplanet science. And as Ross just mentioned, recently we've just had first light with a laser frequency comb that we are busy commissioning. We're not exactly sure yet when this is going to be ready or the kind of precision we're going to achieve, but it is expected that it is going to lead us to around the 1 meter per second, perhaps better when it's available. It's actually currently a workhorse instrument for poorer weather and bright moon conditions. The new kid on the block is our spectrograph. This takes the salt wavelength coverage to 1700 nanometers. It's another IFU-fed instrument. Spectrograph is in a cooler box in the under the telescope. And it's compressed of a science IFU, and there's also a sky fiber, sky bundle IFUs. Currently, doing shared risk observations for the community, and it's full on science observations for the next semester, which is the 1st of November, 2024. And if you want to, for those of us that are more familiar with what it would look like on sky, this is more or less what it can look like on sky. And it's a similar footprint to the slit mask IFU in the optical, so that they're comparable. My main focus of the talk today was about what exactly does SALT do in terms of training the next generation of astronomers in terms of HCD. So we are a part of the curriculum in the National Astrophysics and Space Science program in South Africa. We also get lots of visiting students, international students as well, also come and visit. And we also have a long-standing, I call it program, but it's not really, it's more like an open invitation for students and postdocs PhD students and postdocs to join nighttime operations at the telescope for a week. So they sit in the shadow with a SALT astronomer, they see what kind of science observations we do, they see how the telescope operates, how the Q schedule operates. There's an additional opportunity for postdocs if they are local, or students if they are local, to train further, and then potentially, if they're a postdoc, they've already got a PhD, they may be able to carry out observations, their own shift on SALT for their week. And if they're PhD students at SALT, they can act as SALT operators. What's in it for them? Well, they get a really good training and understanding of how the telescope works, and with a fixed altitude telescope, this is not a small thing. Better understanding of the instruments, better understanding of the Q, they can then get to write better proposals, they get to write better science cases. They already know the community, and their names are known also to the community when they get the data through the night logs, and they get to be better researchers overall. We all win. What's in it for SALT? We again have better researchers, and we also have more observers or operators in the pool should we need them. So it's a kind of win-win situation, but it also gives them the confidence to. Can I put it back on, please? Sorry, 2 slides ago. I was nearly there, home run. Yeah. Okay, thank you. In terms of African countries, Mariana also mentioned slightly. So with the South African astronomical community, as mentioned earlier by Ross and Mariana, we have about 50% of the time on SALT. And that is a fair amount of time which we actively use. But in 2022, the South African steering committee discussed and allocated up to about 10% of the time available to the of the South African share to the wider African community to lead proposals on SALT. We announced this through emails via AFAS, via SALT newsletters, and in our regular call for proposals. And the uptake was slower than we anticipated. We kind of thought the community would be sitting there going, yeah, access to SALT, and then there would be like a flood of proposals. We received one proposal from Namibia, and that was actually through collaboration. So it was an existing collaborator that also had access through from Namibia. So in 2023, we again advertised this in a talk and into the newsletters, and we still kept with the same Namibia collaboration, but no new takers. So in 2024, I attended a workshop in AFAS workshop in Morocco in April, where I gave both a presentation on SALT, highlighted the opportunity to the astronomical community, and also did a very short workshop on how do you use a telescope like SALT, what can you use with it? And I also attended very recently a science conference, AGN across continents in Durham in the UK, where we also had very high African participation. It was amazing. And there was an unconference session that was also held on SALT and how do we make better use of SALT. And there were a lot of ideas coming out of that unconference. And it looks like as a result of all of these, we find one large Pan-African large science program coming up. So I'm super excited. And that should be like a starting point. I think when it comes to fostering collaboration, one thing I've learned is one, you kind of have to be there and demystify it a little bit. Otherwise, it's a remote thing somewhere else that other people are doing and you're not really thinking about it. Mariana also alluded to the complexities of having very few people to do the teaching. And if we're not engaging with the African community and we're not openly offering our help, then any little glitch, they just don't have the time to go and sort it out. So even though we have a very amazing SALT helpline that are very eager to help, that's not necessarily known to everybody. And so it really does require effort on our part to advertise what we're going. And I'm really hoping that this is the start of a much wider impact in the African community, of which SALT, I think, can play a very important role because it's remote, but it's also very easily accessible. And the data basically lands the next day on your lap. So in terms of tools, it should be really one of the most powerful tools for the astronomical community. And the other aspect is that it's also going to be part of the Intelligent Observatory program and hopefully the African Intelligent Observatory program that we've been talking about today. So in the SALT, even though it is a private telescope, please don't let that put you off. It is available to partner institutions, but also through collaborations and through accessing through buy-in time, but also it is open to African PIs, of which there are many around here at the conference, which is awesome. And there's a very exciting Pan-African large science program that is expected coming in. I think SALT is an ideal spectroscopic survey telescope because it has this large collecting power, able to exchange instruments on the fly, fully queue scheduled. You get your data the next day. We're rapid response for TOOs, and we've got extended our wavelength coverage to 1700 nanometers, and we also have IFUs. So this, and laser frequency comm if you're interested in exoplanets. And I think it's an excellent platform for astronomers in Africa. So thank you.
Thank you very much, Nkarni. Do we have some questions? Maybe I can ask a question. How much is the probability of getting a proposal from any astronomer who is willing to observe in your telescope? what is the probability of getting the chance to observe through your telescope?
You're talking about the oversubscription?
No, if I want to observe through your Sol telescope, how much is the probability if I introduce a program to observe? How much is the probability I can get?
I'm not sure I'm understanding your question. So through collaborations, you would have access to different time allocation committees. So if you have collaborations through multiple partners, you will be able to get time through multiple partners. In terms of probability, the oversubscription changes from partner to partner. So it's kind of difficult. Overall, it's around 1.7 for the entire telescope, but it really changes from partner to partner. So
No, I mean for other people that wanted to observe through your telescope. You mean you mentioned that you have 10% of the time for other people that can observe through your telescope.
yes.
So if I introduce a proposal for observe through this,
Oh, okay.
it's probable to get.
So it will go to the science allocation, the science time allocation committee. They will evaluate the proposal, but it is a high probability that you would be able to get telescope time if the proposal is got a good science case.
Okay, thank you. Another question? So we have to move to the, because we are out of time and we have to move to another. Thank you for the next talk is an invited talk by Professor Munshim M from Korea. And this talk is about Korea Microlensing Telescope Network, the multi-messenger astronomy key results and future prospects. So please go on.
Okay, hi, I'm Myung-Shin Im from Seoul National University. As a child, I was watching TV shows and about the great nature of Africa. So someday I thought I might visit Africa, but here I am, actually for the first time visit to Africa to give presentation about astronomy research using great facilities in Africa. So I'm very honored for that, and also it also shows that how Africa has been emerging as a strong force in Africa astronomy. Okay, so I'll be talking about the KMTNet telescope and also the our research activities using this telescope for mostly on transient science. Okay, so I'm supposed to be moving forward. Can you turn to the next slide? Is it possible to do that there? Okay. Okay, yeah. So KMTNet stands for Korea Microlensing Telescope Network. So it is made of 3 1.6 meter wide field telescope. Each telescope is located at 3 different continents, one in South America, Chile, another in Australia, and another one in South Africa. This telescope is built and operated by Korea Astronomy Space Science Institute, named KASI. This is not my institute, actually. My institution is Seoul National University. And this telescope has a field of view of 2 degree by 2 degree, 4 square degree field of view. It has a BBRI filter sets, and it can go to about 23rd magnitude limit in about 6 minutes in good weather condition. So nice thing about this telescope is it covers a wide field of view. It can go relatively deep. It's located in 3 different continents, meaning that you can observe the sky 24 hours a day. So which is very good for transient science. So KMTNet science cases. The main science case for KMTNet is basically exoplanet search through microlensing, as the name of the telescope suggests. But I'm not going to talk about it. I'll be talking about more on the multi-messenger astronomy and related wide field imaging survey that we have been carrying on. There are also other science cases such as the supernova search, solar system research, AGN galaxy studies, but let me know if you are interested. So regarding the multi-messenger astronomy, traditionally astronomers have been observing the sky using telescope, collecting, photons, electromagnetic wave signals. But now that we are in the stage of studying the universe using other methods of, messengers such as gravitational wave and neutrinos, especially in gravitational wave, that the first detection of gravitational wave signal has been reported in 2015. And since then, the hundreds of black hole mergers events were recorded, right? However, well, that the black holes, as in the name suggests, that they are not supposed to emit light signals, right? So, and then also from the gravitational wave signals alone, it is difficult to localize the event very accurately. Typically, the localization accuracy is about a few hundred square degrees to 1,000 square degrees. Okay, very, very wide area. So due to the poor localization, that the limitation has been imposed for the usage of gravitational wave signals for many astrophysical studies, such as cosmology and study of the heavy element production in the universe. But there are gravitational wave events that produce light signals, namely binary neutron star mergers or black hole neutron star merger events. Because of these events can produce debris that can emit light, named as a kilonova in most cases. That you can localize the event very precisely if you can find the kilonova associated with the gravitational wave events. So people have been trying to localize the gravitational wave events through optical or near-infrared follow-up observations. And however, that the wide search area is very wide, hundreds to 1,000 square degree, as I mentioned. And also the kilonova are faint signals, about 10 times fainter than supernova. And also they decay fast. Like after peak luminosity, it decays in a day or so. So it is difficult to catch such events. And also transient events, we don't know when and where they happen. Right? So KMTNet is basically ideal for this kind of research because it has wide field of view and then 24 hours coverage. What? Okay, in this regard, well, we started working on this kind of subject in 2017 when there was a gravitational wave event called 170817, which means that the event happened in 2017, August 17th. This was a first binary neutron star merger event, and it also was detected in gravitational wave, and then later on in gamma ray and UV optical telescopes. We used also optical telescopes in around the world to search for to study these optical counterparts. And before that, we have been using KMTNet as a AGM monitoring study, but with this event, we actually started using KMTNet for the multi-messenger astronomy. So this shows the KMTNet image of the optical counterpart of the GW170817. Left is the kind of image, image, and then right shows the KMTNet SAAO, the KMTNet SAAO image of this transient taken on August 18 here. And then later on August 22nd, showing that it has faded, but the color, if you look at them, very closely, it has become from blue to kind of red. So the kilonova signal, actually, it decays fast, but it changed colors very much. So we did a BVRI multi-wave lens monitoring of this event, and that event, the light curve was fitted very well with the kilonova model that includes wind component. So we kind of confirmed that this was actually a kilonova, and it was published as a Nature paper. And actually, the event happened in the time that the Australia cannot observe, but South Africa Observatory could have observed. So if the same kind of event happens again, at the time we were not very prepared, but then probably the SAAO could be the first place that could discover this kind of optical transients. Okay, we also studied the host galaxy of this event. Since we have been following up this event for a couple of weeks, we stacked the images, and then we were able to obtain, the extended halos around this elliptical galaxy, host galaxy named NGC 4993. And after subtracting smooth light profile, and you have this kind of merging-like feature in this elliptical galaxy. So it's kind of post-merger elliptical galaxy. Motivated by this study, we started actually the officially proposing to do multi-messenger astronomy program with the KMTNet. So we have been doing this since late 2019, and we also, for the period of 2024 to 26, we have got several hundred hours of observing time to do this. So I will show a couple of examples that we have been doing with this time. So one is the S230815.8. This is a supposedly neutron star black hole merger event that happened in May 18th, 2023. This happened during the engineering of the LIGO-Virgo-Kagra observing run. And it's supposed to be at around 200 megaparsec away, and then the localization area was about 460 square degree. And the observation started about 3 hours after the alert, not because that we was lazy, but because we were kind of waiting for more updated signal, localization map. So most of these events, localization area have been covered by KMTNet, and from the north, because it was too close to the sun, that people could not observe this event. And we found about more than a dozen candidates, transients in this event, and this is the observing frame, and then we had reference images. Difference images, you see if there's a transient, you should see a object here, and there's a kind of interesting counterpart here, where the galaxy host galaxy candidate was this luminous distance of about 200 megaparsec, with the projected distance of this transient from the host galaxy is only 16 kiloparsec. So there was an interesting candidate, but it was discovered too late, so we don't know the nature yet. Here's another example. This is 240422 ED. This is another neutron star black hole merger event with a smaller localization area of about 260 square degree at the distance of about 190 megaparsec. We also covered most of the this localization area with KMTNet. We have also found tens of transient candidates here. And we have obtained the light curve. And also one of the events was interesting. It had a light curve somewhat similar to that of the GW17 OS17 event. But later on, that the long-term curve was actually deviating from that. And also thanks to the David Bakri of SAAO, we were able to obtain salt spectrum. It didn't show anything very, very special, conclusive about this event. So anyway, these kind of examples shows the potential of the SAAO facilities, for the multi-messenger astronomy studies. And to find transients from the newly observed images, you need a reference image in advance, right? So that you can compare the new image and the old image to see if there's a transient. Because to do that, we have been performing something called KMTNet Synoptic Survey of Southern Sky. We call it KS4. This is about 6,000 square degree BBRI imaging of the southern sky, where the imaging data are relatively scarce. And many KMTNet time has been used. And this has been carried out with many Korean astronomers, and also in collaboration with the SAAO astronomer, and then also somebody in Swinburne. So basically, we tried to image. This is the south celestial pole, and then this imaging area is something like that. The orange area suggests that, so that the regions that has a BVRI coverage is then completed. And we try to reach about 2023 magnitude, and about with 2 accents in, and then SAAO has contributed about 50% of the time, and then SSO and CTIO has contributed the rest. So KS4 scientific purposes, as I said, it's mainly for providing reference images for KMTNet observations for transient search. But also we are also doing the search for active galaxy nuclei at high redshift, also for doing the galaxy evolution study by finding many galaxy clusters. So interesting example is this GRB 230378. This was a kind of the GRB event, gamma ray burst event, with second highest gamma ray burst energy fluence. And KMTNet, where we did KS4 observation, so we already had the KS4 reference image. So we triggered this TOO observation, and then thanks of this KS4 reference image, we were able to identify the optical counterpart of this GRB event, and we were able to use this data to study the nature of this GRB, which turned out to be later that it's an interesting GRB with a kilonova signature. We are also trying to find high-risk quasars at around redshift 5.5 with KS4 data. So like a UGRIZ filter combinations, it is difficult to find quasars at around redshift 5.5. This is kind of the known high-risk quasars, number of known high-risk quasars, and there's a kind of trial or gap in the high-risk quasar search. Right? That's because that the Lyman break is kind of passing just through the small I band filter curve. So with the BVRI actually light curve, the filter system, since the I band filter width is very wide, that it's actually very much suited for finding redshift 5.5 quasars. So we utilize this KS4 data, and also they combined the data with the Vista hemisphere survey and the WISE data sets, and have been able to identify 3 promising high-risk quasar candidates. So hopefully we expand the search area to much wider KS4 area, and then maybe we can constrain the bright end of the redshift 5.5 quasar luminous function to study the reionization and the bottom budgets for the early universe. We are also searching for clusters. We have identified about 1,000 galaxy cluster candidates using KS4 data. So I will not talk too much about it here, but here are some examples. So looking into the future, now that currently that here is the BNS merger, detection horizon, and then right is the BBH binary black hole merger detection horizon. But with the new detectors in maybe decades later, that this horizon will expand to very, very early universe, and hundreds and thousands of such events will be detected. So I think the multi-messenger astronomy will flourish, and then facilities in Africa would have a very great opportunity to capitalize on that gravitational wave astronomy development. So to do that, in terms of collaboration, we have a gravitational wave EM counterpart Korean Observatory. This is a global network of small telescopes, and KMTNet is a part of it. KMTNet in South SAAO is too. And so I think that there's a global effort going on to find the optical counterparts of gravitational wave event, and I think that's a really good opportunity for Africa. I would like to just introduce one of our facilities for the 7-dimensional telescope. This is a multiple telescope system made of 20.5 meter wide field telescopes. So the idea is that to use each telescope to look at different wavelengths to do spectral mapping of the sky to find the transients and identify their nature very fast. This is constructed near Chile for the El South Observatory. So basically, in each pixel, we will be able to obtain low-resolution spectra of objects, in the entire field of view. And then if there's a transient, such as kilonova, then through the spectral, shapes that we will be able to identify it is a kilonova or not. So basically, in one shot, we have about 60 million spectra in this field. The telescope is already operating with the first image taken in October last year. It shows the field of view of this telescope. This is an NGC 253 galaxy that we have taken with this telescope. So basically, we have spectrum for each object, every object in the sky here. So anyway, here's a concluding remark. So KMTNet in South African Astronomical Observatory has been playing an important role in multi-messenger astronomy. I I think it will play also an important role in future. And MMA, multi-messenger astronomy, will flourish in the next decades. So global collaboration will be very, very important for MMA studies. So I really look forward to be working with the, many astronomers in Africa, and then hopefully can build new facilities such as 7DT in also African continent if the opportunity arises. Thank you.
Maybe you have time for one or two questions. Okay.
Thank you for your talk, but I would like to ask one question only. What is the accuracy of your interferometer measuring the gravitational wave difference?
Oh,
yeah.
Accuracy.
If you compare it to LIGO, for example.
LIGO. Well, actually, I'm not a gravitational wave expert, so I cannot say. Yeah. But with the compared to Berger or LIGO and Berger, I think that the localization area will be very, very small. So they expect like a cosmic explorer or Einstein telescope that I was talking about. Yeah.
Thank you. Yeah. Thank you a lot.
Another question? Maybe ask one question. What is the possibility of including other telescopes in your network?
Well, I'm kind of open to suggestions, but the important thing is probably how soon the observation can be triggered, the data transfer smooth or not, and those kind of things. I mean, I'm kind of very open to including more facilities, especially in the maybe African continent.
Because we are in Egypt, have some team working on same transient observation, so I think they can cooperate with you working in these observations.
Yeah, I hope so. Yeah.
Okay. Thank you. So we have to move to the last talk of today session. The session, Professor Stephen Wanger, ready? And his talk is about the atom telescope enabling simultaneous multi-frequency observation throughout the entire electromagnetic spectra in Africa.
Hello, thanks very much for staying. So this is the last talk that keeps you from lunch. I'm briefly talking about the atom telescope in the context of enabling simultaneous multi-frequency observations throughout the entire electromagnetic spectrum in Africa. And that is on a facility. Am I supposed to be able to go on now? So, of course, now to be moving.
think these problems might arise from the hybrid program. Maybe you have to take care next sections.
Could probably start telling you something a little bit about the talk that I remember, but I'm not quite sure whether that's useful for the people who actually attend remotely. There we go. Okay, so this is about ATOM, which is an automatic telescope for optical monitoring, which exists near HES, which is the High Energy Stereoscopic System, a facility near the Gamsberg in Namibia. It is a telescope which has been operational now for a few years. It's actually an old telescope. It was built in 1975, 0.85 meters, so it's not a big one. It was one of the first alt-azimuth telescopes that were computer controlled. It was built by the Zeiss company at the time in order to promote the idea of actually driving this, and has lived then for a few years in Heidelberg. And 2004, we decided to refurbish it and turn it into a robotic facility for observations at the Hess site in Namibia. Until 2006, we were actually operating it as a remotely controlled telescope. In 2006, we then turned it into an automatic facility, and since 2013, it's a fully robotic facility. Occasionally, we do go back to automatic mode for certain observing modes. Until 2019, we've been observing with a single-channel CCD multiband imaging facility. Since 2014, we've upgraded the detector to enable high-time resolution astrophysics. And in 2019, we changed the instrument to now provide dual-channel multiband high-time resolution imaging and polarimetry. The program is largely to target observed targets that are observed by the Hess telescopes. We actually follow every source that is observed with Hess, either during that particular night, during that particular block, or during that particular season. We do observe potential IAU gamma ray sources in order to trigger the Hess telescopes. So those are mostly taken from the TEFCAT, the catalog of TeV detected sources, the 4FGL, the Fermi source list, and any TOOs that's currently being explored in the various channels throughout the virtual observatory. And we're open to guest programs, and most of those that we have conducted in the recent past were on stellar occultations. The facility actually, as I said, lives at the Hess site. So if you're looking at the left panel, you see the Hess observatories, the telescopes pointing away of you, nicely blending with the Namibian ground, Namibian soil. The small band of telescopes towards the top left panel is a set of optical telescopes, and the largest of those is the Atom facility, which you see in the central panel. The little cylinder-like dome, which is to the right in the central panel, that is the former Rotze telescope, which is currently being refurbished by Dave Buckley to come to life again. The right-hand panel shows you the computer rack that actually drives the telescope, and it's living in that shelter that you see in the central panel. As I mentioned, we have actually turned the instrument now into new facility with a dual channel. Shows just a word on the instrument here. This is a facility where the light actually in this particular diagram comes from the bottom. So it actually hits a dichroic that you can either move out or replace by a mirror to either feed two cameras, or either of the two cameras that you see over here. The blue channel actually goes off the side and does imaging in various bands, and the dichroic, the red trichroic, the red arm actually feeds a polarimeter, which you can actually use or not use and go to straight imaging with a telescope, with a camera that's actually enabling high-time resolution astrophysics. So just a few images about the optics. This is the dichroic. You can nicely see that the blue arm is reflected off. The right-hand panel gives you the polarimetric optics. The filter wheels actually feed both of those channels, and you can actually see that in the optics arm, we can actually replace the dichroic by a mirror or by a free passage, and we can rotate the polarimetric devices. The instrument control box is normally, of course, open for robotic observations, but of course, there's a manual mode for manipulation for tests and control. This is just an illustration of the polarimetry that we do. We are operating with a Savart plate and a retarder splitting off the two channels by about 14 arc seconds. And we can actually go to any details, so we can actually go for a very small number of different polarization angles, or any set of polarization angles that we wish to take. And an illustration of the instrument in polarization tells you that over the years, we've always stayed below 0.1% in the instrumental polarization for that particular facility. The computer-controlled telescope, of course, comes with a cloud monitor to ensure that we're actually always staying safe. So there is a fisheye-fed optics that actually goes to a color mass CCD for 3-band photometry. This is nearly the entire sky that you see on the right-hand panel, and the little circle actually closes on a box which is not perfectly visible to the left-hand panel over here, with a red channel, a green channel, a blue channel. And the lower right part of that actually shows you the 3-channel image that we actually take. Every image that we take of the entire sky is then searched for point sources, subtracting the diffuse emission, and for all of the point sources which are marked in red over here, we do the 3-color photometry. That actually provides us with an optical control for atoms, so we are able to spot clouds very easily and can then close down the facility in case that happens. We actually operate as an extinction monitor for the HESS facility, where we need to know the degree of extinction for the gamma ray showers in order to be turned into a proper quantitative estimate. And we can also use the facility for transients, and we have actually detected novae with this facility as well. Now, this particular sky monitor, together with the weather station, if you're looking at the left-hand panel over here, are part of the robot that actually controls it. So we control the sky monitor. We have a watchdog with the weather station. Both of them then tell the instrument and the telescope whether they should continue to operate or not. And any one of the chains that you see in the left-hand diagram then, of course, splits into a sub-channel. I'm just showing you one example over here for the telescope control and the instrument control for the various channels that we are actually using. This facility, as I said, is robotic, so it actually starts out every night with a scheduling, which is done automatically, feeding the various channels of observing data or the various observing programs that I mentioned in the beginning, coming up with an optimum schedule for all of those observations. But if and whenever there is a reason for diverting from that, which are either TOOs that are coming from externally or TOOs that are triggered by the HESS telescopes or TOOs that are auto-generated by our own facility, then the schedule can automatically be changed. And this is just one example where one particular blazar has been spotted in that night to be sufficiently bright that we would actually want to follow it. We actually triggered automatically to the HESS telescopes in this particular case, and knowing that HESS would then stay for the remainder of the night on that particular target. Of course, ATOM also stays for the remainder of the night on this particular target, and you see that this will then be automatically observed for the remainder of the night. So this is just one such example for robotic scheduling. Now, just a few words on the various results that we obtained with this facility. As I mentioned in the beginning, it's mostly for multi-frequency work. So in particular, actually combining gamma ray astronomy and optical astronomy. And one of the points here, of course, is that we would want to come up with a trigger facility for the gamma ray telescopes, which actually is interesting in its own right. But along the lines, we actually discovered a few things that we had not originally anticipated. To the light panel, you see in the top a light curve in gamma rays. So that's from the Fermi satellite, which of course nicely has the opportunity to observe 24 hours a day and 365 days a year. The bottom panel gives you the corresponding optical light curve. And of course, we've got the seasonal variability, not being able to observe this source when it's behind the sun. You see that the source varies pretty much similarly in both of those channels throughout these 2-year periods, but every so often the flares actually are not as similar as you might have thought. So the various flares are actually color-coded in the two images, and you see on the right-hand panel, which is plotting the gamma ray flux against the optical flux, that it doesn't really look like, as you might expect in case these were all sort of textbook examples of inverse and synchrotron self-Compton flares. So if you actually have optical flares which are synchrotron emission, you might expect the inverse Compton emission that is observed in the gamma rays to basically trace it, but that is not necessarily the case. So the various flares here are color-coded, and you see the magenta one pretty much actually goes up and down, both in the optical and the gamma ray channel. So this is what you would have expected. But then there are flares like this green one over here, which basically stay with a constant gamma ray flux, but they actually very pronounced flares in the optical band. And there are things like the black one, where you see not much of a change in the optical band, but you see a very pronounced gamma ray flare. So why that actually is and what that actually means, of course, is interesting in its own right, but it does make the triggering of the gamma ray telescope with this particular optical facility in one channel only a bit of a challenge. Now, this is where the multicolor photometry comes in handy, because we actually find that part of the reason is that the various optical flares actually do have very different colors. So this is one further example that I would briefly like to illustrate. So to the left hand, you actually see now observations from a single night on a particular source that had been triggered in the previous night by ATOM as being an AGN, which is actually undergoing a flare. With that, of course, we turned the observations for that particular night entirely for that on that target. We also alerted our colleagues in the Northern Hemisphere, so MAGIC was observing the source at the same time. You see the gamma ray observations that were taken by HESS at the beginning of the night. Then for the remainder of the night, they were followed by MAGIC. So this is the color coding in the two things, and you would believe in first instance, this is one single flare going up, going down. But interestingly, if you look at the optical channel, it looks more like two different flares, one nicely comparing to the observations taken with HESS, another one during the period when the observations on the Northern Hemisphere took over. And these two flares actually differ in their color behavior. And so this is an interesting illustration that we had not anticipated earlier on, where gamma ray observations in different colors come in handy. For that particular source, I'm actually giving you a color magnitude diagram over here. You see that occasionally two flares are very similar in this respect, but in other instances, both the slope and the 0-point offsets for these flares are different, which of course means that every individual flare has its own individual nature, which of course is not so surprising after all, but in the end, it actually allows us to do more quantitative work on the individual flares that we would want to follow up. Just a word on high time resolution astrophysics. Of course, this is no news for everybody for anyone who is interested in stellar mass black holes, where you of course are very well aware about the fact that you need to have high time resolution. The interesting thing is this is also true for very massive, supermassive black holes as well. So this is an observation of a particular quasar, 3C279, taken over a course of a little less than a quarter of an hour over here. And the sub-minute time scale that you see here happens relatively rarely, but it's very relevant. Of course, millisecond timescales in solar mass compact objects are very well known. But to first order, you would expect the timescale to actually scale to mass. And given the fact that 3C279 is a billion solar mass black hole living at a redshift of 0.5, the second timescale variability here actually intrinsically turns to something which would be nanosecond timescales if you were able to scale it down by black hole mass. So it's another interesting area where observations with this facility actually revealed quite new interesting insights. So in summary, I'd like to say that ATOM is a fully robotic, small-size telescope with versatile instrumentation. It is devoted to, and as I hope I have illustrated to you, still competitive, despite its small size, in time domain science. Robotic, of course, doesn't mean that it comes in carefree. So there is a lot of work involved in maintaining the facility and repairing issues that happen every so often, in upgrading software and hardware. And that requires actually control by experts as well. It is actually important for HIS as a gamma ray facility. It operates as a trailer, as a trigger, and as a tug. And is relevant for the for the standalone science of this facility, which is to a large extent in blazars, recently in novae, microquasars, sources of very high energy emission, which are time variable. But it partners in with other multi-wavelength facilities. We've partnered in a couple of instances in the recent past with Meerkat, and we intend to extend this multi-frequency coverage where we actually bring in the African radio, gamma ray, and optical facilities in line in order to study time domain phenomena. For special projects in time domain science, for instance, rare TOOs such as microlensing, stellar occultations, and the like, we're as well open. And we're actually open for more collaboration. So if you're interested in co-using ATOM at any point in time, come and talk to me. We're open to do as much as we can when we are not already devoted to the science that we do for HIS. And with that, I'd like to very briefly sneak in the invitation to join the HIS booth that we have set up in the exhibition hall as well. Thank you very much.
Good chance. Okay, Mike, please.
Hello, thanks for the talk. I'd like to understand better the instrument that you have. It was a double channel camera, if I understood well, with a polarimeter after the dichroic separator.
Yes.
So how do you manage to achieve a 0.1% polarimetry accuracy after a dichroic?
We move out the dichroic.
Okay, so it's when it's in polarimetric mode, it's just
we can exchange the dichroic either against a mirror and taking the whole light off.
Okay,
or we can entirely remove it and then go straight to polarimetry.
That makes more sense. So what's the field of view of the camera?
10 arc minute.
10 arc minutes. Okay.
I mean, we're not aiming for a large area because we're really devoted to point sources for which we do high time resolution astrophysics. So there's no need for us to go to high.
So what is the positional accuracy that you achieve with HIS?
Well, with HIS, our positional accuracy is not, I mean, it's typically of the order of 10 arc seconds, but we always know at which source we are pointing. So we actually know what point source it is. So any HIS source is a point source for us. Otherwise, there would be no point in doing time domain science.
Well, sometimes if you have TOOs, you might not be.
True, we need to know the position of the TOO well enough. But again, sort of like even with HIS, even with a gamma ray telescope, you can pinpoint sources to 10 arc seconds.
Okay, perfect. Thank you very much.
And we are 10 arc minute feet. So
Stefan, you showed some results for PKS 1510.
Yep.
Did you also get polarization during? Yeah.
Yes.
Okay. Good. Thanks.
Any other questions? So thank you. So before closing this session, I have to thank you everyone who produced his talk today, and we are sorry for these technical problems we faced today. And I have to announce that we have other 2 sessions today, one at 1:30, the third one at 3:30 p.m. this afternoon, and all these about site selection and protection. And also we have other 3 sessions tomorrow, and the last one at 3:30 p.m. tomorrow. We'll have a discussions for more than 30 minutes. So please try to attend these sessions and joining us in our focus meeting one. Thank you very much. 30.
You hear me? Oh, you can't hear me. Oh, did you hear me anyway? Yeah. Okay, because I have a teacher voice, so that's okay. Good. Thank you so much. We're going to be concentrating this session on astronomical site selection and protection. And our first speaker is Edward Graham, and he's going to be talking about an overview of site testing and site characterization as applied in the search for an astronomical site in Kenya. And it's an invited talk. You have 20 minutes.
Thank you, Connie. Good afternoon, everybody. So the search for an astronomical site in Kenya project originated probably about 20 years ago. It was after the SPY conference in Glasgow in 2004 that Richard Vaughan, whose brainchild it was about trying to build a telescope in Kenya, was developed. And along the way, we've picked up David Buckley and a few others, as you can see. Now, forgive me, please, if I've left off a few names or a few logos. It's been quite a long journey to date, but it's been an enjoyable one. And we've still got a while to go yet. Could we advance one slide, please? I don't think this is... It was working a minute ago. I believe the problem was caused earlier by it not being able to advance PDF files. So actually, I uploaded a PowerPoint version of my document and sent it by email. And please believe me, it was actually working 5 minutes ago. So here we go. Okay, good. Thank you. I think I'll just say from now on, next slide. Is that okay? And you're able to advance for me, please? Thank you. Thank you very much. So, of course, the best place for astronomical viewing is in space. And that's why the James Webb Telescope is up there and Hubble has been up there and so on. But the problem is cash, loads of money. Because at the last look on Wiki, it was $16 billion for James Webb. And even TMT was only 1/10 of that, a magnitude less, $1.5 billion. Apparently, the ELT is only at 0.45 billion euros at the moment, which I find it quite hard to believe, but there we go. However, of course, we are landlubbers and we are stuck on the surface of the Earth, and we have this thing, this thin blue line, the atmosphere between us and space. And In the case of Kenya, of course, we're talking about education and training, and that's very much on the surface of the earth. So that's where we'll keep our feet today firmly on terra firma. Next slide, please. So a wee refresher. So if you're an astronomer, please just fall asleep for the next few slides. But just a wee refresher. Whatever it is we're looking at in space, the light arrives at the top of the atmosphere effectively as a parallel wavefront. The atmosphere breaks it up and distorts it. And it's distortions in the refractive index of the air, microthermal fluctuations on a scale of just millimeters, that could create distortions in the refractive index. So it's exactly the same as looking at a swimming pool that's been slightly roughened from above. We see these flying shadows, and they have patterns to them that can be quite mesmerizing looking at them, or looking at them in slowed down motion. It's exactly the same, except when the swimming pool becomes calmer, we just see a more constant refractive index, just for the whole water column. Okay, next slide, please. So it's equivalent to looking through a swimming pool, because the atmosphere is a fluid too. Again, there are lots of different atmospheric sort of constraints in optical astronomy. I don't want to go through all of these. Essentially, it's to do with clear skies and stable atmosphere. Just one or two of them I'll mention here. You'll be familiar with more or less all of them. PVW, or IVW, as it should correctly be called from a physical point of view. Americans like to call it PVW. I'm speaking in German now. Precipitable water vapor, it's the amount of water vapor in the atmosphere, and of course water vapor absorbs very, very strongly in the infrared, but the correct physical name for it is integrated water vapor. As for summaries of discussions about all of these different parameters, look no further than Mark Sarazen's 1997 publication of his PhD thesis, and later on my one there in 2008. One thing both Sarazen and myself didn't consider, and is much more important nowadays, are these two. No XWEX. What's XWEX? Extreme weather. And almost every day we're looking at the news and we're seeing flash flood here, storm there, gale there, collapse of a glacier here, whatever. Extreme weather. And we have underestimated that. Meteorologists and climate scientists completely underestimated it. We cannot keep up. Weather forecasting today, models cannot keep up with extreme weather. It's becoming more frequent and they're becoming more severe than actually our worst case scenarios. And so it's not going to be extreme weather that disrupts, well, the probability of an extreme weather event disrupting on-site a telescope is less than the effect of extreme weather disrupting the infrastructure, cutting off water, cutting off electricity, cutting off road routes, cutting societal problems, and so on. So these are compound events that will influence our future, rather than the actual deterioration weather at an astronomical site. It's what happens in the infrastructure surrounding it that will cause the problems. And another thing we have underestimated is wildfires. And if we only need to look at this summer in Canada and last summer in Canada, where even at the other side of the Atlantic in Scotland, we had our sun dimmed out one day by the smoke from the wildfires. And if you'd seen the pictures of New York last summer, where the sky went orange from Canadian wildfires thousands of kilometers away. And this not only affects, of course, air quality, it's releasing loads of more greenhouse gases. It also affects, from solid deposition and so on, and atmospheric opacity and so on. Next slide, please. Again, I don't want to go into any real detail about the astronomical viewing indices. As astronomers, you'll be very familiar with all of them, like CN squared, which is just the integrated sum of the refractive indexes in the atmosphere. It's, again, like looking through that swimming pool. Photometric night fraction, the amount of cloudiness or clear skies, and seeing is probably the one that's most widely used. The main point I want to make here is we're looking across a huge range of scales, 10 to the power of 11 at least, to 11 orders of magnitude. So we're talking about time scales of milliseconds, we're talking about physical lengths of millimeters before energy is dissipated into heat, right up to global Rossby waves, which are the big atmospheric waves that circle the planet continuously. There's about 6 or 7 Rossby waves that traverse the planet at any one time, which you can see on global weather maps. And so one single model cannot provide us a solution. It's way beyond our means. Even in amazing nanotechnologies today, we cannot do that. Next slide, please. So just going back to the very beginning, in the 1990s, it was ESO started getting bugged by when they thought Paranal was by far the best site in the world, median seeing 0.5, 0.6 of an arc second. Then they chopped the top off the mountain, and then they built the VLT in 1998. And then they were getting median seeing of 0.91, 1.1 arc second, and they started to get worried or intrigued, or should I say even obsessed by questions such as, does a better site exist somewhere else? And could good sites become worse? Now, how on earth were they going to approach this? And by coincidence, climate scientists were developing a new product at the same time called reanalysis. And ESO decided to capitalize on this reanalysis. So next slide, please. Good, so what is a reanalysis? If there's a word I want you to take home today, it's reanalysis. Because reanalyses are the most accurate picture of the global state of the atmosphere at any one time, including now, but also for periods back into the past, typically to the 1950s or so, and especially since the advent of the satellite era from the 1970s, because there are millions of satellite measurements taken every day that get incorporated in the global observational weather the global weather observational system. And when we add these into a numerical model, such as the European one here, ECMWF, the observations are constrained, the errors are reduced by Kalman filters and processes which minimize both the random and systematic errors in observations, and you end up with what is a reanalysis. And then you do the same thing for periods in the past. You get all old written records from weather stations. Before digitization, you digitize them. You get records from weather balloons going right back for nearly a century. Old satellite data stored on tick-tock tape, you know, the ticker machine tape and so on. And airplanes and whatever you have, and floating buoys and ships and everything else. And you add this into the model in a sophisticated data assimilation process, and you get what's called a reanalysis. Next slide, please. Good. So those of you who watch the news or surf social media sites related to the weather and the climate, you may be familiar with seeing maps like these, global maps. This is just an example created by the University of Maine, what's called a climate reanalyzer. There are hundreds of them around the globe online, and you can plot the weather for any particular day, the day of your birthday, to see where it's warm relative average or cold relative average, where it's dry relative to average, where it's wet relative to average, where it's stormy relative to average, and so on and so on. And there are plenty of websites. This is just one example. And these are all based on reanalysis data. Next slide, please. So, as I said, ESO wanted to capitalize on the reanalysis revolution in the late 1990s, early noughties. And so they invested in a PhD program at the University of Freiburg in Switzerland, where I was. And we developed a software tool called FreeOwl. OWL, of course, from the overwhelmingly large telescope, which was the idea for which eventually became the ELT. And this was a specific web application written in Java for astronomers to use, to make it easier for astronomers to access. And we created 45 years of global weather data, every possible weather parameter, global coverage. And we even created other data sets that weren't actually in the reanalysis, such as 22 years of aerosols data from the TOMS satellite sensor, and also seismic layers as well. And this went into this Java online sort of application, and astronomers around the world were able to use it. Next slide, please. Okay, so I just want to show you one very brief and simple example from FreeOwl. There are many others, and this is just cloud cover. And FreeOwl provided answers to some of those questions that were perturbing ESO. And some of those are found near to Africa. So I thought I'd show you a few African examples here. And actually, interestingly, the least cloudy place in the world above 2,000 meters is not Chile. It's not Chile. It's right here. It's in Egypt. It's in Sinai. It's directly above Mount St. Catherine's in Sinai, is the least cloudy place in the world above 2,000 meters. I'm not saying anything about the stability of the atmosphere, but just that at least that's what the 45 years of data from Friol indicated. Similarly, many of you might be familiar in South Africa, but Gamsberg in Namibia is an absolute excellent site as well, and that has very low cloudiness. And of course, there's the Canary Islands, but also, of course, the Atlas Mountains in Morocco as well are excellent sites. At 3,000 meters, would you believe it, the least cloudy place is actually above St. Helena Island at 3,000 meters, but there's no mountain going up to 3,000 meters there, unfortunately. Next slide, please. Okay, so we talked about reanalysis in the global picture, but of course, in order to try and resolve the different scales and scale down across that 10 to the power of 11, there's 11 orders of magnitude. We've got to go down several orders of magnitude. We first go down to a regional climate model, an RCM, which I'll give you an example of in a minute, and then we can even downscale from an RCM, usually in statistical terms, to the sort of local area. And a regional climate model is known as an RCM, a global climate model is known as a GCM, and a local model, they're usually parameterizing large eddy simulations. That's what LES stands for. Next slide, please. So here's an example just of a weather model that I run, WRF, WRF, Weather Research and Forecasting Model. It's open source. It's freely available from NCAR in the US. And here the flow is from left to right. It's flow over a small hillside, actually, near where I live in Scotland. And I've just plotted two parameters that are related to atmospheric stability and turbulence, the Richardson number here and the Laplacian, which is the acceleration or deceleration of flow. And we can see to the lee of the mountain, well, it's not even a mountain, it's a hill, of course, in Scotland. But we can see more purple colors there indicate greater degree of instability and turbulence. And similarly here, we can see more vivid colors just to the lee of the flow over the hill, where we see increased deceleration or acceleration of flow towards an area of either convergence, which is air being compressed, or divergence, which is air being stretched, which of course create turbulence and variations in the refractive index of the air. Next slide, please. Okay, so there have been lots of studies in the past decade or so, particularly in the last 5 years with the rapid development of AI, artificial intelligence, and machine learning. Just a few examples here. Osborne and Sarrazin perhaps is the most 2018 was perhaps the most successful study using a GCM to predict and viewing parameters, astronomical viewing parameters. Some less successful than others. Turchi et al. Showed that AI just could not work with data from the Mauna Kea Weather Center, 20 years of weather data. And in fact, persistence was actually better at forecasting seeing than the AI could actually do. The main point I want to make about it, and one thing that I think we need to concentrate on in the development of AI and ML, is that it's a bit like making a photographic time lapse. So let's say I went outside onto one of the big, nice buildings here and looked at the clouds. It was cloudy yesterday, it was cloudy this morning. And I took a photograph, say, every hour. And then I animated those photographs over the day. My animation would be very jumpy, wouldn't it? You just see cloud and then a bit of sun and then cloud. It wouldn't be very fluent. But if I took a photograph every 10 seconds, and then stuck them all together and made an MPEG file, I'd see a lovely smooth evolution of the clouds over time, whether they're dissipating or decaying or growing or whatever they're doing, or making lovely waves or whatever. And the problem with MET models is the integration time, which is the time step between one frame, and then you solve the equations of motion and so on, all the different equations in a model, to the next time is typically tens of seconds to minutes. And that's way too long. That's way too long when we're talking about scales of millimeters and milliseconds. So it's not possible. It's not possible at the moment. So we still need to rely on statistical or empirical rules for the time being. However, I think AI and ML should be more promising in making linkages within the turbulent cascade between the outer and inner scales, because we have a similarity of pattern across scales. I've yet to see a good study that does that, actually. So I think that's an opportunity there for someone to try and do. Local weather knowledge is still key. Local weather knowledge is still key. You know that from your weather forecast when you look at your app and you think, oh, lovely sunny day, and it pours rain or whatever, or vice versa. Local weather knowledge is key. Next slide, please. Okay, so I said I'd talk about Kenya as well. So forgive me again, please, if I have missed out the logo of your organization or institution here. I've tried to remember everyone. Please forgive me if I haven't, if it's not there. So the Kenyan projects have been known by various acronyms over the years. It started off with SASCA and then Saskia, Search for an Astronomical Site in Kenya. More recently, we've adopted COTI, Kenyan Optical Telescope Initiative. Next slide, please. So for those of you who don't know Kenya, Kenya straddles the equator, and there's a big gash through Kenya in the western half. It's the Rift Valley. And this is actually an altitude map here, and you can see the gash of sort of reasonably low level terrain of 500 meters to 1,000 meters, and the escarpments on either side where mountains stretch up to 2,000 or 3,000 meters. It's much more humid on the western side, near the side of where Lake Victoria is, and towards Lake Turkana up in the north. And it's much drier in the northeast of Kenya, where it's effectively semi-arid stroke desert. Next slide, please. So we initially started identifying. We identified 13 initial candidate sites. Richard Vaughan, as I said, initially at the start, identified these, and we then used the reanalysis to look at the actual what the reanalysis indicated the weather parameters would be at each site, and then we followed them by site visits much later on. Much of this work is summarized in a paper in Theoretical and Applied Climatology in 2016. As you can see, the altitudes of some of the sites all range between about 2,000 and 3,000 meters or so. Next slide, please. So just specific, very quickly, the data that we use reanalysis at the best, most resolute, most high resolution model was called ERA interim at the time. That's since been superseded by something called ERA 5, which will soon be superseded by ERA 6. There are lots of other reanalysis produced by institutes. For example, in America, there's the NCAR reanalysis, which I think there's going to be a later talk about that one as well. Anyway, so it's a 31-kilometer resolution, 60 levels, and 6-hourly temporal resolution. We also used 2 years of Met Office Africa limited area model, which is very high resolution, 12 kilometers with 70 levels. But it was quite difficult to work with. You couldn't resample, that is, you couldn't zoom into an area of interest and discard the rest of the data. You had to use it all at once, so we just used 2 years of that data. Next slide, please. So just a couple of maps, just to give you an idea of the sort of data and what we were dealing with. And this is actually a map of integrated water vapor across Kenya. So that's just to remind you what integrated water vapor is. So here's the surface, and this is altitude in units of pressure. And when we go to a certain height, like 700 hectopascals, which is about 3,000 meters or so, we just integrate all the water vapor up, and we come up with a cumulative value. And as you can see, the red colors here are where it's moister, and the blue and green colors are where it's drier. And we can see the Rift Valley showing up really well there in that resolution, and around Lake Turkana, and of course towards Lake Victoria too, where it's much more humid. And the drier peaks of Kilimanjaro and Mount Kenya, of course, although they're cold, they're also very dry, because it's so cold and the air can't hold nearly as much moisture. And it's pretty dry in the northeast of Kenya too. Next slide, please. Perhaps the most important parameter we need to look at in Kenya is what's called the vertical velocity, because the vertical velocity dictates, it's the up and down motion of air, and we don't want a vertical velocity greater than a few millimeters per second, because anything more and we're greater than the inner scale. We want a speed that's like the famous phrase, big whorls of little whorls that feed in their velocity, and little whorls of smaller whorls, and so on to viscosity. We want scales below a millimeter or 2 per second, and that's what we're looking for. And we actually have quite a stable atmosphere above 3,000 meters in Kenya. This is actually 5 years of data, and this is actually the degree of vertical velocity. And we can see bright colors in the lowest 3,000 meters or so. This is air ascending quickly and descending quickly, averaged, which is convection, daily convection, and so on, and nighttime, morning, this sinking back down. And of course, we have the seasonal effects too, which are very prominent there. But by and large, for most of the year, the atmosphere is really quite stable above about 3,000 meters. So that's the kind of critical height we're looking for. Next slide, please. So eventually we narrowed it down to 3 or 4 primary sites. Mount Kulal, just east of Loyangalani, east of Lake Turkana. The 2 Old Donyos, Old Donyo Nyiro and Old Donyo Mara, on either side of South Hore in Samburu County. And Mount Kenya, although it's much moister in terms and much cloudier, the northern slopes are the driest part of it. And it's also, critically, it's within easy reach infrastructure-wise of Nairobi. It's just within 3 hours, whereas the Old Donyo Nyiros it's at least a day's hike, even when you get to South Hore. There's no road or anything up to any of the summits. Next slide, please. So we actually visited some of these peaks by helicopter 5 years ago. So that's myself there, Jacob Lukupe, a local community leader in South Hore, and that's David Buckley there. And what Jacob is actually taking an infrared measurement of the atmosphere. We had these little infrared thermometers where we measured the emissivity of the sky temperature. And that would help us determine how dry a particular site was. Unfortunately, Mount Kulal is heavily dissected, whether by heavy rains in the past or earth movements, we don't know, but it's not a suitable site at all. It's heavily gorged and so on, and wouldn't make a suitable site simply from a practical point of view. Next slide, please. Old Donyo Nyiro, however, looked much more promising, and it's actually higher than we originally thought. Google actually corrected the altitude, daft logic. It used to be estimated as 2,750 meters. It's actually 2,860 meters now is the correct altitude. And there's a plateau on the summit. It's much more suitable for some sort of telescope. Although, as I said, we'd need some sort of facility, some sort of pathway or roadway up the mountain if it was to be explored further. It's also within mobile Safaricom, there's a direct view down to the transmission tower in the valley below, so it would be possible to send data back down. Even at a very low rate, weather stations don't use huge amounts of bytes at all when they're sending data. Next slide, please. So just to summarize overall, the best sites in Kenya are northeast of the Rift Valley. And one thing actually I didn't mention already is the sort of the northeast easterly prevailing wind, which comes off a relatively flat terrain to the east of these mountains, particularly Old Donyo Mara and Old Donyo Nyiro. And that minimizes the degree of mechanical turbulence that could be created. If you've got a site that's downwind of rough terrain, it's more likely to create perturbations and in the atmospheric flow. We believe, according to the reanalysis, there's at least favorable conditions for 8 or 9 months of the year. Dust is certainly an issue in northern Kenya, but again, as I showed in that slide of vertical velocity, the inversion is very close to the highest summits. It's around about 3,000 meters. Our most favorable mountain is 2,800 meters. We're tentatively close there. As I mentioned already, remote areas are difficult to access. We have 3 automatic weather stations purchased kindly by the University of Edinburgh. They've arrived in Nairobi, and hopefully in 2 weeks we're going to install the first one on the slopes of Mount Kenya as a dry run for installing them on the more remote sites. We also have been promised an Atmoscope that's currently lying in Namibia, and we hope to maybe give that little push in the direction of Kenya in the near future. I mentioned already, sorry, I'll just come back to the AI and ML in a second. We'll have, thanks to DARA, the DARA project, we'll have an African master's student who, once we get the weather data telemeter down from the summits, We hope to employ an African master's students to analyze the weather data and compare them with the ray analysis to see if the ray analysis is actually telling the truth. Because remember, it's only a model so far. And then finally, just or penultimately, AI and ML. I mentioned this already. There's so much fuzz and buzz about AI and ML, but we need to know, we need to think about it. What is it it's doing? And we don't have any observational data for Kenya. We have no analogs. So we cannot train an ML to learn from it because we don't have anything, it doesn't have anything to learn from. And because we don't know if the reanalysis is true, we need to validate it with observational data first before we can profit from AI and ML. And also by definition, AIs cannot deal with new unprecedented extreme weather because it hasn't happened in the past. It's new and it's unprecedented. So we don't have an analog for it. So the AI is blind to it. So we need to be careful. Okay, finally, climate change. I won't go on. Well, I've already mentioned that in terms of extreme weather. We are now the weather makers. We are now the weather makers. The Hadley cells, which control where the best sites in the world are today, such as in Hawaii, Canaries, Chile, southwestern parts of Africa, these Hadley cells are expanding. They're moving at half a degree, up to half a degree per decade. That's 5 degrees in a century. That's a lot. So the potential for the deterioration of some sites, but the improvement of others could be envisaged. Next slide, please. Just some of the references there. And next slide, please. And thank you very much. That's my contact details if you want to get in contact with me. Thank you. Yes.
Kenya is the most promising. But I also just want your comments on, when you alluded to it in your last point about climate change. And paper that came years ago, really predicting quite worrying future trends.
Yeah.
How much later science is world. Wonder how much more data do you know for sure how those
I don't think it's possible to say for someone like Kenya as to what climate's. I mean, even climate scientists have been surprised by the increase in extreme weather and so on, which really the worst case scenarios weren't predicting. So in the case of Kenya, we don't actually have observational data yet. Even when we do, we need to correlate that with things like El Nino and La Nina and the Indian Ocean dipole and so on to find out, what sort of weather conditions correlate with each dipole of the each weather system in index, and only then would we be able to tell if there were, for example, predicted changes due to global warming in the evolution of El Nino or La Nina. Only then would we be able to infer, and of course not with certainty. There would be a great deal of uncertainty. So I think we're still at very early stages in that regard, but there is the potential for major upheaval, and we're to quote Donald Rumsfeld, it's a bit of a, we're dealing with unknowns here. It's unknown unknowns rather than known unknowns.
Sorry. Sorry. Our next speaker is Abd El Farin Marcos, building large telescopes and site tests. Can we have the first slide for him, please?
Yes, please. We checked it. The break. We checked it. Yes.
There you go. Oh, you want to put it in presenter mode? Or
Yes. Full screen, please.
We could advance it from there, I guess, if it's all right with you. Okay, okay.
Building of large telescopes and cycles. Really, it is not new subject, but I'm going, yes, sorry. This is not new topic, but a lot of persons wrote need. But the problem is the arrangement of these points or these topics. Yeah, you put, okay. Therefore, the main point here is 5 essential points. Astronomical part, and on most of cases in building observatories, we concentrate in this point. Environmental, geological, and a lot of persons neglect this point. Social factors and risk factor. Really, these points must be considered before putting any study for establishing or mounting any telescope. The first one, basic location. Sometimes we choose a location without testing the geographical properties of the place. For this reason, maybe it is ready to be earthquakes or unstable place. Therefore, you put a money in nothing. The second one, why I'm going to build this telescope. Therefore, we need the size and design of this telescope. The optical system, if I need it, in that case, I must fix what are the components which I'm going to do it. What is it? Please back again, one slide. Okay, no, the next one. Okay, monitor and tracking. This point is also very, very important, but a lot of persons not looking for it. A stable and precise mounting system is required. Because if you couldn't mount it in strong situation, in that case, you also mounting something which is not used. Instrumentation, and in most of cases, build our optical telescope. But after that, we're thinking in what are the devices and instruments we'll be choosing. But really, I must, from the beginning, when I'm trying to establish a telescope, in that case, we put what we need, what we are going to do, what our plan in that stage. The control system. What is the meaning of control system? Are we able to make it robotic or make it suitable for using AI, for new technologies, or just we doing it just to use it in the time being? But we must, when establishing any telescope, in that case, we put in our consideration, the optical one is need at least 6 to 7 years to form your mirror. Therefore, in that case, this technology which I choose it is suitable for the coming interval. It will be suitable in the second generation of astronomer or not. The next one, please. The budget. This is a critical point because you may starting building your telescope and after that, you didn't find the budget to complete. Therefore, you putting plan 1, which is I going to complete all the observatories my own, or I putting some other condition, which is I must share another countries to help me or to share together to do this telescope. And this also the collaboration with other observatories or other experiences in it. Next, please. The environmental condition. Really, we're looking for the conditions which we are building the telescope at that time, but we didn't know what is happening in the future interval. Therefore, we must expect the future changes, for example, in the atmosphere, in the light pollution, in the cities, which new cities. Scientific object is the main object. Sometimes we putting some topics and we cannot approve it. For example, if I saying, for example, I'm going to study minor planets in very not suitable area. In that case, this is project not be done. Therefore, we must fix essentially our project. Yes, please. The sky condition, and this is the second part, which is very, very important because without our sky, without our dark sky, we cannot establish a telescope. And here in our observatory, now a group is working in studying this light pollution and the effect of new cities. Clear sky, it is controlled really by multi-system. I'm going to just clarify one of them. And there is another part which must be taken in our consideration later on. low light pollution. For example, if we're choosing a desert and pure desert, and we didn't expect that there is a new cities surrounding, which has happened nowadays in our Kotamaya Observatory. It works for long interval of time. But at time being, we cannot say that the Kotamaya Observatory is the best observatory in the Middle East as the previous situation. Is it right? Therefore, this point is very important. Stability and atmospheric condition. We looking for a visit, 2 visits, 3 visits for the place. And after that, we said, for example, it is the best place. But I didn't study it during more than 2 or 3 years to see the variation in the atmospheric condition. Therefore, if we found it stable for 2 or 3 years consecutively, in that case, we can say this suitable condition. Please, the next slide. Low atmospheric turbulence. Sometimes we are looking in a day, for example, I made a visit for a week for this place, which I'm going to establish on mountain at the scope there. And I found it very stable during this week. Is it a good indicator that there is no turbulence in the atmosphere? We must consider it for long. Low humidity. Yes, it appears for desert in most of cases low humidity. But who is sure that this situation will be? If we have a civilization around it, therefore pollution and humidity will be high. High elevation. On most of cases, we are looking for the elevation, but we are not looking, is it the future situation, what is happening? Why no extension for the human person to transfer to this area? The next one, please. The low atmospheric interference. In that case, also, we didn't consider this one. I'm not exceed in explanation because I know that you knowing better than me, but I'm just putting a technique for what I'm going to do if I would like. The weather stability, also this is one of the conditions which is very important. Accessibility. Maybe I choose place, very good place, excellent place, but I can't go to my observatory easily. In that case, the work will stuck in a day and we cannot complete. Please, the next one. Legal and regularity. Sometimes we choosing a place, and after that, in most of countries, if something happening politically, therefore, this place will be forbidden place. Therefore, we must choose. Is it will be available all the time, or maybe in the future due to what I'm seeing here? Okay, the next one. With respect to sky, I know that a lot of you portal scale, please, if you push on the blue link, yes, from you, your position, yeah, no, in the blue part, yes, this portal scale, yes, push, yes. I think all of you, you know, this scale is really very astonishing scale and useful scale to do the degree of darkness of the sky. The first one is one, which is the best situation. And if you are looking for the last one, and it is known because this is very old system, but it's still very, very useful system. Please push the arrow again. There. Yes. The second one, sky quality meter. Really, previously, we check the darkness of sky by using photometer. Photoelectric photometer, and this is designed by Egyptian group and manufactured by American company. It is very accurate, very useful, and we're having multi filters to check the sky completely. But it needs hard work. But nowadays, the sky quality meter plays this rule very fast because you can fix it in one place and follow it all over the year. Therefore, we can have a good idea about the sky. And there is a poster in tomorrow, I think, about the Kotamaya. We made this study on Kotamaya Observatory. For this reason, I'm not just forcing that. We can use simple device to know very strong reality. Yes, please, the next one. Naked eye. Most of persons, when you're saying that naked eye, you're saying that you are crazy. Why? You are looking by telescope. Why is that? Look, if you are be sure that the naked eye can observe very tiny object in the sky, in that case, will be sure that your telescope is going to do its function. Therefore, naked eye observation also very important point. Astronomical seeing conditions. The seeing conditions are the natural condition, which is all the time. Darkness indicates the darkness and the brightness and the pollution and so on. But really, also, I'm repeating, is the stability of seeing is happening or not? Light pollution map. Really, I'm doing the light pollution now. But you must put on your map the prediction for the future years. Because, for example, if you have say, I'm going to Kotame Observatory, for example, we choose it as very far from the citizenship and also very dark area, very high. But after interval of time, the new cities surround it. Therefore, Kotame cannot do all the functions of observatory. The next one, please. Astronomical data, and also I can talk in front of all astronomers about the visibility and darkness and so on. Sky quality index, really most of us neglecting it, because IDA is a factor, very important factor and useful when you try to build it. It is ranging from 0 to 25, and this by this one can control the quality of a sky. Is it qualified enough to do observation or not? The next, please. Sky brightness, one of the factor. The cloud factor, maybe it is clear in a interval, but it is too near to a sea or ocean or something like that. In that case, the clouds will be. Transparency, also because a high humidity means low transparency. Seeing condition, okay, is a sky quality index. Okay, the next one. Final comment. Many research conducted optimized locations choices, but in most of cases, we neglecting the mathematical process. Therefore, if we use multi-decision analysis, this procedure, by the way, there is only one person use it in the last interval in 2023. I'm writing the reference after the representation. The second one, analytic hydrology process, which is AHB. And also for geophysical conditions, there is GIS. All these programs are very useful and can be used. And nowadays, most of astronomers do statistics as well. These programs really are useful. I check it in one place, not mine, but by other persons. And their comments are very useful in most of cases. But no one can neglect the sky consideration and methodologies adopted to selection with a primary focus on 10 criteria detailed in this study. Please, which is previously mentioned. Yes, please, the last one. All these references are talking about these points in details. Really, I collect and summarize it, hoping that putting a category, in particular, we are nowadays put the building stone of our big telescope at Sinai, and we hope that we are going to follow all this procedure. I think our colleague is starting the first steps, but we are going to complete at the end. Thank you for your attention, and thank you also for the organizer for this session. Okay. I'm going to details because due to time, but we can discuss after that because we're having the same place and you know a lot of details about that. Thank you. Yes.
I'm going to ask this question to you. I'm wondering how long does it take to identify a site from scratch that might be good for tangent.
Okay, you can. But you can't predict what is bigger because
to say that this place is suitable?
I would say decade. I would say, yeah, at least a decade. I think in the case of, for example, ESO and Arizona's, they knew about Arizona's for a long time. These maybe it's right now. Things are changing. So even like yes. Also experience, therefore, cannot be done by one person, is the first point. The second point, you have to choose it randomly and exactly.
Okay, so hi everyone. First of all, I would like to thank the organizing committee and Focus Meeting One to accepting my presentation to present it here in the General Assembly. My name is Mohammed Darwish. I'm researcher at the National Research Institute of Astronomy and Geophysics. I'm a specialist in radio astronomy, but I'm also have some experience in size selection and size maybe optical also astronomy. So I'm gonna show you today on how the impact of the meteorological and also the seismological parameters on how to select a site in Egypt, special case. Okay, so the next slide. So this is my outlines on this presentation. Okay, next. So generally, I'm talking about some important parameters in the meteorological as well as the seismological parameters, including air temperature, relative humidity, wind patterns, and also AOT, in addition to the seismic activity. And also one important parameter is the light pollution. I will include in like a fast way because we have another colleague will talk about it in details. Okay, so next. So I mean that all the people here know the importance of studying meteorological and size and maybe seismological impact on how to select a ground-based observation, and actually it's crucial parameters to build a new telescope, especially in the time of climate change and so on. So I'll focus on this in this topics and these parameters. Next. Let's start with the current situation in Egypt. So this is our Katamia Astronomical Observatory, and this is the location. So actually, Katamia is still the biggest optical telescope in the Mina region so far. Actually, we did a lot of work, and we discovered a lot of objects using this telescope so far, and still working. But let's see how the meteorological parameters and especially the light pollution affected on this telescope. Next. Okay. Next. Good. So I'll focus here on specific parameters. So let's say that the air temperature, by the way, this data is using we are using the ERA 5 data analysis to extract this figure, and this is as you can see yearly average data for this sites. So you can see that the air temperature is dramatically taking away to high, and also the perceptible water vapor, which is important parameter, especially for the radio astronomy people to actually if they want to observe the H2O, the water meter, and so on. So the total cloud coverage is quite good, not too bad. Okay, so relative humidity is also okay for the Katamea. So far the Katamea is good to observe, okay, no problem. But let's say, what about the light pollution? Next. So if you go to the various online site, you can see, and you can see that this is the telescope site. You will see in a zoom in, okay, next slide, this big issue. So if you look at this, from 2012, the amount of light pollution here is increasing incredibly. So actually, based on this information, and you search for a candidate to host a new telescope is a must. Next. Oh, we started our search by using the DEM with a very high resolution. Okay, so I want to highlight that this work is a part of a big collaboration and staff in Egypt and in different university, and also people from Trieste in Italy. So this work is a part of a paper. I'll show it after by the end of this presentation. Okay, so you can see that this is the digital elevation models. Next, for Egypt. So after this, we put some conditions to select the sites. Okay, so for the first, it should be high. Okay, to avoid the turbulence of the turbulence of the atmosphere. Let's say more than 1,000 meter. Also, the second parameter is the accessibility. The third parameter is to be away from the cities to avoid the light pollution, scattering. Okay, and based on this, we got around 8 sites. Again, next. Okay, so we compared our site with one of the very interesting publications by Aksaker in 2020. Okay, so we find that most of our candidate sites have a good let's say value in Aksaker, except this one. Next. And we eliminated this one. So we focused on 7 sites in Egypt. Okay, so the 7 sites. First of all, we looked at the Zenith, that's sky practice, from the online internet data by VERS. We find that those are excellent in terms of the light pollution, and this is a very important point for the optical observation. Next. Again, the air temperature for all the sites are good. Yeah, they're varying, but it generally are good. Okay, next. Also, we discussed or explored the direction of the wind direction and its velocity, and we find that it's all in all direction, which is good. In all the year, so it will decrease the turbulence around the region. So this will make your telescope all the year stable. So next parameter is next. The next parameter is the number of clear nights for each site, and for this we consider this reference to that the cloud coverage less than 25% per year. So this is our result. We found that an excellent values for the site one. We have more than 280 nights, and for 6 and 7 we have more than, or we have almost 290 clear year per the year, clear nights per the year. Okay, so all of this also are taken from the ERA 5 data. Next. An important actually parameter is the AOD. The AOD is the measurement of the total aerosol distributed through a column of air extending from the Earth's surface to the top of the atmosphere. And here is that a full image of Egypt for the AOD. So those are also our candidate sites are located here. So you can see that this area, which is Sinai, is very good in terms of the AOD. Next. Okay, so seismological parameters, and it's important. And sadly, I can say that this parameter is very important due to the effect of it. So you can see that the collapse of one of the let's say historic or radio astronomical telescope in the world, which is the Arecibo, which is collapsed due to an effect of the seismic activity. So you have to consider this parameter in our study and to search for a new telescope. So I think most of us want to pay around $1 billion, and then let's say earthquake come to destroy all what they do. So we have to consider these parameters. Next. Okay, so to understand the seismicity of the region in Egypt, we put let's say a map for Egypt, okay, and try to gather all the online data from different catalog, and this is the source of this catalog, to find that if the strength of the magnitude that happened during these areas on Egypt, and this is these are the strengths. Of course the red one is the higher one, and so on. Again, sorry. Next. Okay, so we focused now on our 7 sites. So for the 7 sites, we found that we have one site here is a very good and have a low seismic hazard, and 2 in Sinai have a high seismic hazard. In the region of the Hordaga or the Red Sea, we have also one low seismic hazard, and the other 2 intermediate or moderate, and 1 high seismic hazard. So this should be taken in consideration. Okay, next. To understand all the process, we combined all of these parameters, and let's say we did an overscore for all of these parameters. This ends that these parameters from 1 scores from 1, 0.9, 0.82, 0.85, and 0.0857. Those are the scoring for those parameter. We actually from the 7 we find that 4 are good for accessibility and so on. So we concentrated on this 4 site. Next. Okay, so just to remember you that all of this work and more are done in this paper. So I invite you to take a look for this paper for more details. Next. So I have to acknowledge the people working on this day, on this paper, and actually both I mean some of them are attending here in this meeting. I would also acknowledge the general support of the AFAS and the organizing committee to support me to I present my work, and actually without their support I wouldn't be able to attend. Finally, thank you for your attention. I hope in time. Thank you. Yes. Sadly, you have to. Okay. Turnas, اتفضل.
Excuse me, how does symmetrical hazard change dramatically within 10 kilometer?
Okay.
Second question, please, do you have map for water table, turbulence?
Okay, so this work is actually focused on some parameters like the air temperature, humidity, and so on. But actually, it could be extended to let's say include air turbulence and
good day to all of you.
other parameters. But I think for this only we just mentioned those parameters. Actually, it takes too much time and too much paper to introduce this. For the seismic hazards, we actually I'm not specialist.
I mean, how change this lot of change in hazard within 10 kilo?
Okay, so it's not related only to the point that the earthquake happened and the
Good day to all of you. I am Youssef Hatch and I am very much pleasure to present my research proposal in front. I will introduce my research.
I just said I'm not expert in the seismic points. You can
I will introduce my
authors of these papers and can contact and you can contact with my college from Trieste or even from Nariai.
Okay, thank you very much.
You're welcome.
Any further questions? One more question? Okay, well, let's thank our speaker again.
Thank you.
Okay, we have as our last speaker here, Dr. Youssef Hatch, and he's going to be talking about characterizing and comparing astroclimatic parameters in the free atmosphere of the Mina region through NCEP and NCAR reanalysis, a comparative study. So is he here or he's online? Is that an online talk, sir? Say it again, please. You're supposed to be in person? Okay. Well then, if he's gonna come and we have time for him, that'll be great. But we were thinking, Dr. Yosri and I were thinking, or Yosri was thinking, we should do a panel of the three people who have spoke, and they could answer more of your questions. We have somebody, for instance, online who already has a question for the first speaker. So. Oh, he has a video. Oh. Oh, I apologize. Okay. We'll still try to have maybe 10 minutes of question and answer session. So, but go ahead, right ahead. He should have about 15 minutes, I guess, for his talk. Hard to get that done, huh?
Good day to all of you. I am Youssef Hatch and I am very much pleasure to present my research proposal in front of you. Today my research topic is titled, Characterizing and Comparing Astroclimatic Parameter in the Free Atmosphere of Mina Region through NCEP, NCAR Reanalysis, a Comparative Study. I will introduce my research subject by qualifying sites for the installation of an astronomical observatory. This operation crucial is carried. Good day to all of you. I am Youssef Hatch and I am very much pleasure to present my research proposal in front of you. Today my research topic is titled, Characterizing and Comparing Astroclimatic Parameter in the Free Atmosphere of Mina Region through NCEP, NCAR Reanalysis, a Comparative Study. I will introduce my research subject by qualifying sites for the installation of an astronomical observatory. This operation crucial is carried out in several steps which can be summarized in 2 steps, pre-selection and installation of the instruments on the best pre-selected sites. However, there are several problems that hinder this qualification. I will cite in particular. Impossibility of carrying out measurement campaigns generally linked to the problem of accessibility. Absence and discontinuities of measurements. In our study, we tried to find other alternatives of astronomical site testing for hosting an observatory and therefore be able to save time and the cost of observations. The solution proposed in our study for the MENA region, Middle East and North Africa, is based on the one hand, choice of NCEP, NCAR Reanalysis System database as an alternative to direct measurement at the observation site. And on the other hand, the use in our study of new approaches which currently apply to the characterization of astronomical sites and which generally relate to several site selection factors instead of using the classic scheme. In this works, we have carried out 2 studies of sites characterization in the MENA region by using astroclimatic parameters obtained from reanalyzed data covering 2 periods. Based on several works, notably that carried out by Gesum et al. In 2014, we already undertook a site pre-selection study on a main list comprising 18 sites in the MENA region. This allowed us, after a scientific classification, to reduce the main list to 6. For the first period, we are today undertaking the comparative study of the 6 pre-selected sites in terms of dynamic turbulence based on meteorological data. The second study spans a single year and covers the same 6 sites from the main examine aspects related to optical turbulence. This work constitutes participation in the pre-selection study of future astronomy observation sites in the MENA region. The main objective of this study is to identify the best location in the MENA region which can be recommended for astronomical observatory installations in several countries of MENA. Then, improving the characterization of sites for the astronomical observation. Finally, is to show the usefulness of reanalysis data for the characterization of sites. In this study, we used NCEP, NCAR reanalysis data which provide global coverage with adequate temporal resolution. The parameters analyzed include wind speed and its direction, height, and pressure. We also analyzed integral parameters such as seeing, coherence time and isoplanatic angle. We proceeded by processing reanalysis data in free atmosphere. We analyzed the different astroclimatic parameters of the sites in the MENA region in order to be able to classify them in terms of atmospheric turbulence. The astroclimatic characteristics of each site were compared using statistical methods, monthly, seasonal and annual, to identify significant differences and understand the particularities of each site in terms of atmospheric turbulence. Cumulative probability distributions and seasonal trends of wind speed at the 200 millibar level were plotted for each site. The vertical profiles of the refractive index structure constant and probability distributions of integral parameters were also generated to visualize local variations. The results were interpreted to identify the most favorable sites for astronomical observations. We present here a brief review of the different parameters of atmospheric turbulence introduced in this scientific research work. We cite in particular the Richardson number, the average speed of turbulence, as well as integral parameters such as seeing, coherence time and isoplanatic angle. In addition, we present the equation translating the Tatarsky model which allowed to obtain atmospheric turbulence data from meteorological data. The topographic map, obtained by processing satellite data, shows the different sites studied and their elevations, Aklim, Klina, Diriba, Mishbi, Saitu and Shams. The colors represent different altitudes, with color bar on the right indicating elevation in meters. Blue areas represent negative altitudes and brown and white areas higher altitudes. The highest areas are mainly found in the mountain ranges, particularly those of the High Atlas in Morocco. To explore the seasonal behavior of wind speed at the jet stream level, we plot the monthly average value of wind speed during the period from 2011 to 2015 for the 6 locations in the Mina region. The 2 sites Mishbi and Shams present the same seasonal behavior characterized by low values of wind speed in summer and high values in winter. The amplitude of the speed variation is the highest. However, the Aklim site presents an inverse seasonal behavior with a low amplitude. It is the same for the Klina site. These differences may result from variations in geographical locations and atmospheric conditions. Indeed, the 2 sites Shams and Mishbi benefit from being close to the Red Sea on the side of Mishbi and the Arabian Sea on the side of Shams. Hence the probable existence of a cold current flow in advance of the seas that helps create a temperature inversion. We present here in the figure the statistical results of the wind direction at the 200 millibar level. The color distributions in this figure represent the scope of wind speed values. For the sites of Aklim and China in North Africa, we see that the wind speed has a single predominant direction, the east component for Aklim and the west component for Klina. The main distribution range of wind speed values is less than 30 meter per second for Aklim and then 60 meter per second for Klina, which is consistent with the statistical results of wind speed indicated by the histograms figure. For the 3 sites Mishbi, Shams and Saitu in the Middle East, the wind speed presents 2 predominant directions, one is towards the west in the case of high speeds and the other towards the east otherwise. Indeed, the winds come in these directions due to the atmospheric flow on a large spatial scale. Now we move on to the parameters related to the aspects linked to optical turbulence, and we will start with the Richardson number. In the figure below, we present the profiles of the inverse Richardson number for each site studied. For the low-latitude sites, Diriba, Shams and Saitu, there are visible peaks for the profiles of Richardson number inverse in the troposphere region, around 14 kilometers, and whose intensity decreases with altitude. The more the value of Richardson number inverse increases, the more the atmospheric conditions are unstable and easily produce dynamic turbulence. For mid-latitude sites, Aklim and Klina, the tropospheric region is between 9 kilometers and 10 kilometers. The intensity of the peaks in this region is very strong for the Klina site. However, we note the presence of another peak of moderate intensity at 25 kilometers altitude for Aklim. In general, we can say that the atmospheric conditions at the Aklim site are more stable than those at other sites. Therefore, a low probability of turbulence triggers in Aklim compared to other locations. The refractive index structure constant is of great importance in determining the force of turbulence at any site. The adjacent figure shows the probability distribution of vertical profiles of refractive index structure constant for different quartile values. For the 2 mid-latitude sites, Aklim and Klina, the refractive index structure constant value increases in the first 11 kilometers with altitude and reaches its maximum at the height of jet streams. The same for the Mishbi and Shams sites, but with a fairly low jet stream height. Between the height of jet streams and 24 kilometers, the value of refractive index structure constant decreases with altitude until reaching low values. For the other low-latitude sites, the vertical profile of refractive index structure constant presents a different behavior, which is manifested by the presence of 2 peaks. The first at around altitude 9 kilometers and the second around 14 kilometers. The variations of refractive index structure constant at the Diriba sites and Saitu are almost identical. Likewise for Shams and Mishbi. This is probably due to a similarity in the topographical characteristics of the site. The seeing is one of the main parameters of high angular resolution. The figure shows the statistical results obtained for this parameter from the reanalysis data for the year 2011 on the 6 sites in the Mina region. The mean, median, and quartile values of each site are also represented in this figure. We note that the Diriba site presents 95% of seeing values lower than 0.58 arcsec with an average of 0.5 arcsec. However, there is a very small lack of seeing value. The same thing for other low-latitude sites which do not have many small values. Thus, we can say that the ICLIM site benefits from periods of the year where the state of atmospheric turbulence is minimal, which is favorable for an imaging observation which is exigent in turbulence conditions. 25% of seeing values at the CLINA site are greater than the value 0.63 arcsec. CLINA has lower sky quality than other sites in terms of atmospheric turbulence. The second parameter of high angular resolution is the coherence time. The temporal evolution results of this parameter obtained from reanalysis data are shown in the top figure. On the bottom figure, we represent temporal coherence distributions, blue histogram, and cumulative distribution functions, red line, from reanalysis data. The mean and median coherence time values obtained from the data for the 6 Mina sites are also shown in the figure above. We have also presented the different quartiles in the bottom figure. About 75% of the coherence time values are above 6.56 milliseconds, 4.95 milliseconds, and 4.60 milliseconds respectively for Diriba, Site 2, ICLIM. Atmospheric turbulence evolves slowly in the Diriba, Site 2 and ICLIM sites which has the largest value of the coherence time among the others, which will therefore allow adaptive optics systems to effectively correct distortions due to atmospheric turbulence. We also note the existence of a continuous period of the year where the value of the coherence time is high for the 2 sites Mishbi and Shams, which is beneficial in the case of using adaptive optics instrumentation. The last parameter of high angular resolution is the isoplanatic angle. The mean and median isoplanatic angle values obtained from the reanalysis data for the 6 Mina sites are shown in the figure above. On the bottom figure, we represent the temporal isoplanatic angle distributions, blue histogram, and the cumulative distribution functions, red line. We also presented the different quartiles. About 75% of the isoplanatic angle values are above 1.64 arcsec, 1.61 arcsec, 1.60 arcsec respectively for Site 2, Diriba, Shams. The effect of atmospheric turbulence in the Middle East site is weak over a large area of the sky. Likewise for the 2 low-latitude sites in North Africa, Diriba and Mishbi. These sites are qualified as the best in the Mina region. The highest value is recorded for Site 2 with a value of 1.64 arcsec for more than 75% total values. That said, the field of vision at Site 2 is very large and the correction carried out by adaptive optics systems would therefore be very efficient. In conclusion, we can say that in terms of dynamic turbulence, 1. The analysis of the seasonal behavior of wind speed at the jet stream level allows on the one hand to quantify the value of the speed and on the other hand to know the periods of the year when there is a low value or a high value of the speed. 2. The Richardson number is unable to quantify the strength of turbulence. It can be considered as a tool to check the consistency of measurements of turbulence that will be carried out in sites not yet prospected. The figure below shows the classification of the different sites in the Mina region in terms of optical turbulence. According to the statistical results, we can say that the best locations in the Mina region which can be recommended for astronomical observatory facilities are Diriba, ICLIM and Site 2. In addition, the results presented here constitutes a potential reference that will enable astronomers to test and develop ground-based optical astronomical telescopes and SAAO instrumentation at the 3 sites in the Mina region. Finally, these results presented here are supplements for further investigation of the site characterization in terms of optical turbulence parameters. This is the end of my presentation and thank you very much.
Questions? But we do have time if the three speakers, if Dr. Graham and Dr. Marcos and Dr. Darwish would like to come to the podium for just a few minutes, 5 minutes or 10 minutes, and answer any questions that people have. Because I know, for instance, for Dr. Graham, there was one question from Evan Irwan Akbar, who asked, are the other two speakers here? Come on up, yeah. I think we need, is Dr. Marcos here still? Okay. Well, anyways, good. For the first speaker, you have a question. Evan says, you mentioned that the resolution of the reanalysis data is not adequate for turbulence in terms of millimeters and millisecond resolution. So what is the best method to validate it? Using radiosonde data and launching balloon, measuring seeing using DIMM and other methods, perhaps?
Yeah, observations, direct observations.
Direct observation.
That's really the only way to validate. There are proxies. As I showed there, in fact, the last talk was talking about Richardson number, although it wasn't, I think the conclusion weren't so favorable. The Richardson number, if you've got a very high resolution model, in the case of the WRF model, which is a regional climate model that you can run down to as low as 500 meters even, and you can have, I typically run it with about 70 different levels in the atmosphere, but you could run it with hundreds. And in that sort of case, you're not directly resolving features in the atmosphere, but you're resolving more of them. And you'll get a result that's at least a reasonable proxy for what you would achieve in measurements. But it's not a solution, but it's a good proxy, and it'll point in the right direction. But at this stage, the only solution is still observations.
Yes, sir.
Nothing about it, but LiDAR, I know, is used for atmospheric studies. Is that something that can give you rapidly what seeing?
I know they use them at airports, David, and yeah, and also wind profilers. I'm not aware of any studies offhand, to be honest, David, that have tried to do that. There may be some value in attempting to do it, but a wind profiler costs about 100 grand, so they're not exactly to a penny. It would be worth actually just at some stage linking up actually with aviation meteorologists, because they know an awful lot about turbulence as well, and turbulence is becoming a lot more of an issue in aviation, you know, due to climate change. So that's another area of potential exploration and opportunity.
I suspect also space ranging, people who are using lasers to find satellites. They do adaptive optics on those systems. So
okay.
That's true.
Yeah. But that could be sort of information that's not readily available.
Yeah, I don't think there are any. There's a shortage of potential and possible collaborations we could make to improve our knowledge in this area. Certainly. To be honest, I don't know enough about them to be able to comment any further, David. Sorry.
Well, we have probably time for another question. Go ahead. So that people can hear you online, do we have a mic at all? Thank you very much.
I want to ask about the lessons you learned from looking at good sites in Kenya, and if we are able to get these lessons in our search for good sites in Egypt also.
I'm sorry, I didn't quite understand that. Do you mean
You mentioned,
extrapolate what we're learning in Kenya to Egypt.
I mean, for looking for good sites for the building new telescopes in Kenya, you mentioned your lecture now, your
Yeah.
talk. We are now looking for good sites also in Egypt.
Yes.
And if we are able to get your lessons, you learn, because we have, for example, an accessibility problem in one of our sites that we can not reach in order to put the site testing instruments. And we started working with only one site. Is it possible to start working with one site and then until we have solved the accessibility problem of the other sites, or no?
I think in the case of Egypt, as Mohammed explained in his talk, I think there are definitely some good sites there. I wasn't aware actually of all the earthquakes that happened near Sinai. So I guess that mitigates the excellent cloud-free conditions. But in Kenya, we've narrowed it down more or less to three or four. And I think it would probably be wise, and we've got three sets of weather stations, which of course we could move to different sites if some of the currently indicated sites don't prove to be as good as we envisaged. Because remember, the reanalysis, as good as it is, it's the most accurate model we have, it's still not truth. And the only way you can validate it is with observations. And it may be that actually the observations at one or two of the sites aren't as good as we expect, but in which case we can move them somewhere else. So yes, I wouldn't put all your eggs in one basket, or eggs in one basket, as the saying goes, to at least survey the top two or three, I think would be wise.
But I mean the other site, we have two sites now. One site is very good and we have road to that site and we can access it easily. The other site is very difficult to access. The terrain of the mountain is very difficult and we cannot send the site testing instruments like DEM and other station and so.
Yeah, I think in that case, you need to use some sort of decision model, as the second speaker was mentioning, this sort of mathematical decision aiding mechanism of some sort. And there are plenty available in sort of desktop GIS which will help you do that. You just need to allocate a weighting to the that reflects the importance of each parameter to you. And different organizations will allocate different weightings. I mean, if it's all about money and time and getting something built as quick as possible, you'll allocate different weightings to something where it's more about training and education.
If we have one side, then how we compare? Compare with what?
If you have one side.
If I have one side only, then how we compare with what?
If you have only one site, well,
in the same point,
well, then obviously you don't have a choice and you've got to go with your one site. But I would still recommend undertaking both modeling and observational studies.
I mean, we need comparison with.
I mean, you can compare with other sites in other countries, certainly that might be at a similar latitude or have similar environmental conditions. But I would strongly recommend that all sites characterization or site selection studies have some sort of modeling and observational aspect to them both, where the modeling can be validated with real observations.
Okay.
Well, we've come upon 3 o'clock, guys, and I don't want to stand between you and your
second-
coffee.
Okay.
But, oh, sorry.
Small question.
Well, if people don't mind.
Excuse me, I have used Mira 2 model. Is there any comparison with Mira 2 model with another model?
I'm not sure.
Would you like him to come up and talk to you about this?
We actually used the
Mira 2 model.
Mira 2 models.
Oh,
okay?
Mira,
yes,
yes,
data.
yes, yeah.
So Professor Nasser asking if
we have another data
Another
to compare
comparison
with.
with another model.
Do we have a more higher resolution data to compare with if it's
The current highest resolution reanalysis is about 15 kilometers or so, but there's a new project called ERA6 that'll be coming out, I think next.
ERA6.
Yeah, ERA6.
ERA6.
ERA6 will be coming out, and that'll be even higher resolution. Yeah, and I think that's going to be out within the next year.
Okay.
You can run your own model. What that is, you can run a very high resolution model, as I was mentioned just in response to the first question, such as WRF, which is the example I showed briefly in my talk. You can run that up to, well, hundreds of, 500 meters, maybe a kilometer resolution. It won't work at any higher resolutions because then you have to start resolving features explicitly, because models don't solve the physics of the atmosphere directly on at the actual scales that, for example, a small little cumulus cloud, a model cannot resolve that explicitly. It uses parameterizations, a statistical technique, to bypass things it can't resolve. So a model can't really be run less than, depends on the type of weather pattern, but less than maybe a kilometer or 500 meters, because now we're getting down to scales such, I mean, where the we're getting close to, the turbulent cascade at Kolmogorov's inner and outer scales, and in those cases you need to actually resolve the features explicitly. But that's a whole new ballgame, it's a whole new type of model to do that.
Okay, thank you.
I think we should say thank you to all our speakers. They may hang around for a couple more minutes if any of you have any questions for them. What I'd like to say to yours, I think it's like.
I know I didn't. Yeah.
So that's something that's very.
Yeah, and it's getting back. I know. Yeah.
And for you, I think it's not just the fact you got like this, but what is the growth we see around with?
Yeah. Hi, Yoshi. How are you? Good to meet you. Good to meet you. Yes.
I was asking.
Yes.
Because we have two sites. Muhammad in his
Okay.
research.
Yes. And the one on Sinai.
One Sinai and one in Red Sea.
Okay. Yes.
The Red Sea site is very difficult to access.
Okay.
The terrain of the mountain is very difficult.
What height is it?
It is about 1,300.
Okay. Yes.
The other one in Sinai is 1,650.
Yes.
So this one in Sinai, we already bought the site testing instruments because it is accessible. The other one is not, it's very difficult to access.
Okay.
So how can we start with one site only and compare the results with theoretical
Yes, you could. If you install instrumentation on the first site and then correlate it, do some multi-regression analysis with the reanalysis, and then go to the second site, get the reanalysis, and then try and go backwards and work out what the observations might be at that site. So reverse the auto regression. So if you
also is objecting about this feature.
No, I don't like.
Yeah.
Because we should compare at the same time.
Yeah.
we will start now. Hi, everybody. I am Zuhair Ben Khaldoun. I supposed to give a first talk this morning, but my flight was delayed. I am sorry for that. I will share this session and where we have 4 talks, about 20 minutes each. We will speak. We will have Warren Skidmore. We're speaking about establishing the scientific and technical aspect of a future astronomical observatory. He's an invited speaker. We will have Constance Walker. She will speak about the protection optical observatory site from the growing satellite constellation interference. And after Ramoto will speak about the dark sky protection in South Africa, potential model for other observatory in Africa. And finally, we will conclude with Federico Di Verno from SKA Observatory to opportunity for Africa and challenge with new large satellite constellation. So Warren is online. You can share your screen, Warren, and the floor is yours. You will have 25 minutes for your talk. Thank you.
Thank you, Zuhair. I'm sharing my screen now. Can you see it?
Warren, we don't hear you.
Yeah, hello, Zuhair. I'm speaking and I'm sharing my screen. Hello. I'm sharing my screen. I'm speaking. Hello, Zuhair. I'm speaking and I'm sharing my screen.
Yes, it's okay now. We're hearing you. The floor is yours, Warren.
And you see my screen? Hello. I'm sharing my screen. I'm speaking. Hello, Zuhair. I'm speaking and I'm sharing my screen.
Yes, it's okay now.
We can hear you.
We're hearing you. The floor is yours, Warren.
And you see my screen? Hello. I'm sharing my screen. I'm speaking. Hello, Zuhair. I'm speaking and I'm sharing my screen.
Yes, go ahead. We are hearing you and we see your screen. You can go in.
Okay, there's a very strong echo, and we were getting several repeated echoes. I wasn't repeating myself, I promise, Zuhair. Thank you very much for your patience. So my name's Warren Skidmore, and I'm ever so sad that I can't be with you guys in person. It just wasn't possible for me to travel. We've had some great talks about establishing projects and why we want to establish projects and where we want to establish them and things like that. And there's a component of establishing a new observatory project that is quite important and has become more important in recent years with new project management techniques that are and new system engineering processes and things like that. And that's making sure that we, from the very outset of the project, we do our best to understand the scientific goals of the project. Exactly what Abd was mentioning in his talk. We need to understand the science, and it's not everything we have to do. There's a lot of things we have to do to establish a project, but understanding the science is very important. There's been a lot of discussion about what's going on in Africa, in the continent of Africa. There's lots of projects that are going on. I'm going to focus on observatory projects, a telescope plus instruments, big projects. But there are lots of instrumentation projects which are going on, smaller scope. And a lot of the sort of things I'm going to talk about are kind of scalable, but my focus is the establishment of an observatory, and I won't repeat this. There's lots of good reasons why a project to build an observatory may arise and be carried out. Mariana spoke very well about those, you know, the international collaborations and cooperations, all sorts of things that come about through building observatories. But one of the things we need to know from the beginning is understanding the kind of science we want to do with the observatory. And there's many reasons for this. You know, number one, it's key for promoting the project. Having some sort of high level you know, grab some science stories that grab people's imagination and excite people. That's very important for promoting any project. And so some sort of high level description of the science goals in some sort of science case, science book is important to have. When you're communicating with other astronomers, you know, the future users of the observatory, they want to know what the observatory can do for them. So if they see science cases that are close to their own areas of science, that's a good thing. And also the development of a science book or a detailed science case, collecting everyone's ideas. That's a very good opportunity to engage with the astronomy community, whether that community is, you know, the astronomers within a country or within a region or internationally. It depends on the project, but building up a science book is a good chance to build a connection with future users of the observatory. And the technical information that you gather when you build a science book, when you capture everyone's ideas, that technical information, what type of observations do they need to do in order to do the science, that's what guides the design of the project. Of course, one doesn't come without the other. You know, if you had no constraints, everyone would want a 150-meter telescope that had every instrument possible on it, built on a 17,000-foot high mountain, and that's not possible. So it's a sort of an iterative process. Have some idea, develop some science ideas, develop some kind of design, and the things go hand in hand. Yeah, one feeds back to the other once you start this process. Now, understanding the science goals is also important for understanding where you can build the observatory. You know, what do you want the observatory to do? If it's a seeing limited optical observatory, you want somewhere that's got lots of clear nights and you know, dark skies. If it's lots of adaptive optics science, you want a place which has very high, very good atmospheric turbulence properties, and you may be less worried about the total number of clear nights. It's different parameters would have different weights depending on what sort of science you want to do. And across Africa, there's a lot of different sites. Each one of them has its own qualities. So you know, you need to know the science you want to do so that you can identify the parameters, the qualities of the sites that you could consider. So when a project is born, when people start to have the ideas, you know, a whole bunch of things need to start to happen. You know, think of some cool science, think of a design. You know, I'm here because I got to know Yosri and the folks that are involved in the ELOT project, the Egyptian Large Optical Telescope project. They have an idea for a design. You know, you can think about the kind of science you would do with that. and once you have a design as well, you can start to think about, how much it's going to cost, the schedule, where you're going to get the money from, start to define this project scope, develop a partnership. If you have a very ambitious project, you may need to spend time building up the partnership so that you have the resources available. And then, there's this thing at the bottom, begin the project integration management. That's how you start a project formally. It's all written down in textbooks. I don't know if you can see my little picture. There's lots of project management textbooks. It's all standard sort of stuff for starting off a project. Now, this list of things, I say, is not a chronological list. They all have to sort of take place. They may not all start at the same time, but they will definitely overlap in time. And they'll often need to be done before you have any significant resources available. So how do you develop a science book and get technical requirements and things when you don't have money to spend on the project? I'm not sure how I don't have an answer for that, but these are the sort of things you have to navigate through as you start a project off. But the number one thing, or the main thing, is really understanding the science that you want to do with this observatory. Now, lots of the partners will have additional goals, and these are things which are not astronomical. It's workforce development and things like that. So those are also factors you have to consider in the larger project. But what I'm focusing on here really is what you do about the science and how you understand, how you gather the information to understand the science you want to do. So in textbooks, you often see sort of pictures like this, very idealized. Someone's got an idea, let's build an observatory, so you get some science cases, come up with a design, iterate it a bit, and the project will go. But this is not reality. All kinds of things happen to disrupt this idealized picture. And something which is probably a bit more realistic is that you have each line here, each colored line represents when I was making this picture, a partner. Might be an institution, it might be a country, but different partners with different priorities. And someone at the start thinks, let's build an observatory, and they start to accrete, build up the partnership and find out what the partners want to do, and eventually, some resources are committed, and eventually, people or the partners align, and you get a nice coherent picture of the observatory. And this is kind of a little bit like this idealized picture rolling along in time. And eventually everyone hopefully will converge, and you can really formally push the project forward. And this process can be quite difficult because everyone has different ideas, different things they want to do, and to get everyone to converge can be very, very very difficult process. So back to this point, having a good idea of the science goals is important. So you need to develop something like a science. I use two terms here, science case or a science book. I work for the 30-meter telescope project, and we have the TMT detailed science case. But I don't like that name because the detailed science case consists of lots of science cases. So, I prefer the term a science book, a big, thick book that has all the science cases in it. And a lot of projects use that terminology. And you have to have, when you start to develop this science book, some idea of the observatory. What what sort of scope it'll have. For the ELOT, 6.5 meter mirror with some sort of imager and perhaps a spectrograph. I'm not sure of all of the ideas, but there'll be some general constraints which will help to guide the science ideas, and that will also help you with developing the idea for how much the whole thing's going to cost. Basically, what resources you're going to need to build the observatory. So when you're building the science book, you can have some broad science areas, high-level science areas, and you don't need to have every single possible science case in your science book. You just need to have some representative cases which define observing capabilities, which will service other areas of science. So you can get going relatively modestly to begin with, and from these science cases, you develop the top level science requirements, and you can use this when you're talking to other astronomers, saying we're going to have this type of instrument, this spectral resolution, this wavelength coverage. These are the sort of top level requirements that you can discuss with the community. So you have to start to have communications, with resources, talking to other partners or potential partners, or people at the university if you're a large institution, and then you also need to communicate with astronomers, and that can take all kinds of different forms, but you have to communicate with them to gather their ideas, get a representative set of science ideas, and like it's an iterative process. Once you've got some science ideas, and you know what sort of capabilities you need or you want, how does that actually feed back into the process? So you are in a sort of a chicken and egg situation. What comes first? The chicken or the egg, the science requirements or the or the science goals? And there isn't, all you need to do is pick one, start the process, and go back and forth a couple of times. So communicating with the community and with all stakeholders is key, and you can start the process off with some fairly modest communications, a workshop, email newsletters, and open calls to the community for input, that sort of thing. And all projects kind of go through this process. They all develop science cases or science books. You can see in the top row here all the different kinds of science books. Most of them are called a science book. And this second row is the requirements, the technical requirements that come out of the science book. And I wanted to note down here, for SKA, for example, the science book is thousands of pages, very technical, almost like lots of observing proposals stapled together. For TMT, it's for my project, it's a very sort of narrative kind of document, a couple of 100 pages long. And then for the new robotic telescopes, it's pretty short, just a few pages long, really, with just some exemplar observing programs to make sure that they define the full scope of observing capabilities that they need. Now, when you're collecting people's science ideas, over on the right-hand side here. Every astronomer has some idea of some cool science they want to do. When you collect that information from them, you must collect the technical information at the same time. It sounds obvious, but you've got to set up a process that does it. And how you set the process up, I'll talk about that a bit more in a moment. But I wanted to give you a bit of a historical perspective. You know, my project, 30-meter telescope, has been around for a long time. These green boxes in the middle show the 4 iterations we've had of the TMT detailed science case, our science book. But looking here towards the earlier part of the project, there were a few ideas, 3 different projects for a 30-meter class telescope that merged to form the 30-meter telescope project. And those, each project had some sort of science book, and we had a science advisory committee that pulled all that together, and it was representative of many areas of astronomy, and they really wrote the detailed science case. They had additional input from all of these early instrument studies as well. Each instrument that was proposed for the 30-meter telescope came with a science case. So they had a lot of information that they could pull together, and the science advisory committee, a group of about 15 people, wrote the first detailed science case. And then a few years later, we revised that, and we wanted to make sure we reached out to as many people as possible. And we set up these international science development teams, very similar to the Rubin Observatory science collaborations. Topical groups, one on black holes, one on exoplanets, one on star formation, galaxy formation, topical teams. And they wrote our 2015 version of the detailed science case. And there were hundreds of people involved in that that gave input. So you need to go through this process of developing a science book. And you have to sort of set some ground rules. Who will be the people that really approve this, the science book? I've got this word here in the top row. They approve it. They may not write it necessarily, but they accept it as a good, valid document. And it might be, at least for the case of TMT, it's the Science Advisory Committee that formally approves the detailed science case. But they get advice from other, the system engineering group and instrument teams, and also the Science Advisory Committee themselves are very much involved in in keeping the document up to date. So when they approve it, they know what they're doing. And you need to have some sort of group that will approve the science book that you develop. But you need to identify one person to lead all that work, make sure it's all coordinated, and each project will have various engineers that start to get involved, or people that have developed projects before, and they can give you help and advice and actually do work on developing project documentation, early project documentation, developing the requirements from the science cases. This is the thing which I find most interesting is what process do you use to collect the science cases and the technical information from the community? How do you do that? So you have to think about who will be providing this information. Is it a group of individuals like the TMT SAC back in 2007, or is it lots of people like big projects tend to do these days? And how do you kickstart that process? Most projects have annual science workshops or something like that, some way of getting people together to discuss science and to contribute to collecting this information together, and then decide on what the science case is supposed to be. Do you want it to be a nice book that you can read, or do you want it to be a very sort of technical document? That depends. Different projects use different versions, different type, different formats. For TMT, it's more of these manuscript. It's a bit like a science paper, but a big one. And everyone writes their parts and puts it together, but these are take a lot of work before you can publish them, and often it's difficult to collect the right technical information if you're just letting people write whatever they want to do, whatever they want. What I would advise anyone doing this is to come up with some sort of something which looks a little bit like an observing proposal, and you can use like a Word document template. That's pretty easy just to set up. People might submit it with fields not filled out and things like that, so you don't have super good control over that. But it's pretty easy to set up, and for relatively modest numbers of people, that's okay.
Can you conclude, please?
Yeah, I think I've got 2 more slides left. I'll speed up a bit. What I would recommend is some sort of web form. Try and set up a Google form, and people can put in the narrative, add some pictures, and put their technical information in, and that's good for lots of people. And then make sure you collect the technical and narrative parts at the same time. That's very important, a big lesson we've learned. Let's see. So this is my last slide now. So just to summarize what I've talked about, when you start a project, you must understand what the science goals are from the early days. And I've got here project promotion and technical information for the project. Those are sort of key areas that's important for. And then in order to do that, think about the process you want to follow that collects together all of the technical and scientific information, and all of this has to be done as you're building up the partnership, doing some design work, thinking about the costs and schedules of things. It's quite tricky, but you do need someone to run the process and you define it, and you have some workshops and meetings with astronomers, and get them to tell you what they want to do with the telescope, and start with that very early. And I think that's the last it. Yeah, that was the end of my presentations here.
Yes, okay. Thank you so much, Warren. And we will let the question for the end of the session, and Connie, you can.
Well, hello, everyone. And many thanks I want to say first to the organizers who have allowed me to present. I'm really thrilled to be here. I'm going to be presenting on the protecting the optical observatory sites from the growing, can you hear me? Yeah, the growing satellite constellation interference. And with me on this venture are the wonderful team we have for the management team, as well as the co-directors or co-leads of all the 4 hubs I'll be telling you about that belong to the Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference, or we affectionately call it CPS. Okay, so next slide, please. Oh, you're not even on there yet. Do you have me up there? It's the second one, Connie Walker, Protection of Optical Observatory Sites. Anyways, I can get going, I guess, while they're trying to get that up there. We're now on the second slide, sir. Okay. So you're going to see an image that's going to kind of astound you because it is of the Earth, but it's of thousands and thousands of satellites presently around the Earth. And what you're going to see in the second slide, thank you. Oh, do I? Okay, yeah, I'll try working with it. The first session, it didn't work so well. Okay, I have the controls. Thank you. That's good. So this particular image illustrates the challenges we're facing at the moment of a burgeoning new space era. And these dots represent the current number of active and inactive satellites, as well as rocket bodies and debris and some other uncategorized items that are up there. And as you can see, there's almost no place on Earth that you can actually be that you won't experience seeing them if they are bright in your neighborhood. And I'll talk about that in a few minutes. And also, there's not going to be any place on Earth that you won't experience them growing over the next few years. And that's what I'd like to talk to you about today, is both the challenges and the solutions of the increasingly large numbers and brightnesses of the satellites, and how they're going to impact our field, and how we as an international community should actually work together to protect our night sky and our field, and for all humanity as well, not just for our field, but for humanity in addition. Let's go to the third slide. Oops, are you not there again? Sorry, I'm trying to progress. Okay, well, this third slide is on the sustainability goals, actually. And let me see if I can advance it. I can't, because say it again, Zohar. No, I'm not. I don't have, well, I can't. They should be sharing the screen. Yeah, there you go. Thank you so much. Sorry about this, guys. This is, I want to direct your attention again to what Mirana said at the very beginning, the first talk, excellent talk. She was talking about the sustainability goals. And with all of the problems that the satellite constellations are presenting to our field, in reality, satellite connectivity has been very effective in providing internet connections to isolated communities. And I have to acknowledge that. That's a fact. And we're not trying to, in any way, IAU has no intention of hindering the operations of satellite constellations at all. But we have to acknowledge as well that this interference is having an impact, a negative impact on our field, and we have to try to work together to mitigate the situation. So let's go to the very next slide, please. Okay, so one challenge that we are facing is an exponential growth in the number of satellites, and over the last few years especially, and these are with mostly the commercial satellites, the LEOs, they call them, low Earth orbiting satellites. And right now we have about 10,000 active satellites that are up there. And then more than 500,000, closer to 1 million of satellites that have been listed to be licensed to launch. And this is mostly with the International Telecommunications Union, and also in the United States, what they call the FCC. And that's a huge number that's going to be impacting our dark and quiet skies. Next slide. Okay. So this is a simulation, and a simulation is by Ollie Hano at ESO, and he did a simulation of 70,000 satellites, which we're very fastly approaching. And in that situation, almost anywhere on Earth, you might have between 2,000 and 5,000 satellites overhead, right? So, and the plot on the right, what you're actually seeing is the brightly lit ones that are coming about right now. It's at twilight. You'll see them in a moment, coming up at twilight and then getting brighter and then dimming again towards the middle of the night and then starting all over again. And I mean, they at twilight, both at night and in the daytime, you'll see more satellites, basically because the sun's hitting, reflecting off the satellites. So, and on the left-hand side, basically you're seeing from space, you're having a veil of satellites that are surrounding the Earth. And the blue dots on the top are the ones you actually see out of the tens of thousands that are orbiting, basically, in this simulation. So it's between, again, 2,000 and 5,000 you'll probably see. Okay, so what I'd like to do in the next few slides is try to capture what impact this is having on optical astronomy. And my colleague, Federico De Bruno, who's in the audience here, will be talking about the radio impacts to radio astronomy in another few minutes. Okay. So most of the observatories most of the observations done at twilight are to search for near-Earth asteroids, right? Near-Earth objects, and also solar system objects that exist between basically the orbits of the Earth and Venus. And these observations must be taken in the direction of the rising or setting sun so that they actually can have a, can be seen. And so the observations of potentially hazardous asteroids require very many detections in order, in a very short discovery window, in order for them to be able to determine their orbits. And so if the data that could help determine the orbit is lost due to some satellite trails that are crossing the image, then we lose the probability determination for collision with the Earth. So this is a very, very, this is actually, if we can go to the next slide again. I'm not paying attention to you guys up here, sorry. Can we go to the very next slide? Yeah, so there's the simulation on the right-hand side, 5 images being combined into one and then having a satellite trail basically obliterate some of the information. So, and then there's 3 other case studies I have here of different kinds of areas of astronomy that are affected as well. Okay, so how, I'd like to talk about a little bit, how are these observatories impacted? And after I go over a general case, I'd like to actually go into a little bit about what I found out as of late from 3 out of the 5 countries in Africa that are being represented here in this session. They have given me some information I'd like to share with you about the impact on their observatories. So in general, though, when a very sensitive optical telescope has an illuminated satellite in its field of view, the streaks that are produced are actually, they irretrievably cause the loss of data. As I was mentioning in the last slide, telescopes with larger fields of view are the more severely affected. So for the narrow field telescopes that view a very small part of the sky, the effect is limited and is predominantly at twilight. So maybe 10% of all their images might be affected. I'm giving a very sweeping guess here. But in general, they can avoid basically satellites if they choose to in that case, right? Or maybe just retake the data if they have to. In the case of wide field facilities, where they are looking at, a good sizable portion of the night sky, you're going to be more severely affected. Here, basically almost all the frames at twilight will be affected, and a few during the whole night. So like Vera Rubin Observatory, you're going to hear me talk a little bit about Vera Rubin. It's part of our family at Noir Lab where I work. And the Vera Rubin in particular will be affected primarily at twilight, almost every image, and then sometime during the night as well. Okay, so this next slide. Next slide, please. Okay, why don't we go to the following slide? Yeah. Okay. So this is a reality we're facing. On the left-hand side, you basically have simulation. Well, they're all simulations, actually, using the LSST camera on the Rubin telescope just as a case study. And they looked at 3 situations. One where it's just a streak that's below what a limiting magnitude of 7 basically is what's being asked for the different industries, to the satellite companies, to try to uphold to be less bright than 7th magnitude. And if you did that, you pretty much have a streak that you have on the left-hand side here, and you could subtract that from your images, more or less, right? You still lose the data underneath it, but at least you can try to subtract it. The middle panel that you see here is basically what the current Starlinks are providing us with a little bit more than the minimum value, which we're trying to still obtain. And so you have some residual streaks you could see on either side that kind of, present a problem. And it's not a very linear streak across, so you can't really subtract it too well. And then you have things like that are coming about more and more, are these communication, the satellites with the direct to cell, huge panels of antenna, phased antennas on the like 8 by 8 meters at least, or 10 by 10 meter platform that is basically totally reflective. And this is what you get with Blue Orca 3. It attained, we had a paper out a little more than a year ago by the center, and it showed the highest magnitude was basically as bright as Vega. So about brighter than 99% of all the stars in the night sky. It was hugely bright. So that's a problem. Okay, so can we go to the next slide, please? So this past week or so, I've been in contact with 3 out of the 5 countries that are represented in this focus meeting. And from Paul Baki at the Technical University of Kenya, he was telling me that he thinks right now there's a very minimal effect of satellites on these various observatories that are listed here. And basically one of each of the countries I mentioned are listed here as well. So, but he did acknowledge that the landscape is changing and that we have to consider what the future holds, right? And that it could be a lot more than it is right now. But right now, for you all, it's pretty minimal. So let's go to the next slide, please. So in this next slide, we had Boskri, and forgive me, Zuhar, if I say his last name not correctly, but he works with Zuhar and the Ukamedan Observatory in Morocco, and he was very kind enough to give some, actually some GIFs, some simulations here that show latitude, or actually the number of observable satellites by latitude on the x-axis, and a function of time going around, as you'll see here. And it's over pretty much almost a week, I think, here he shows. And you can see mostly at the beginning and ends of the night, you see more satellites. Let's go to the next slide, please. Here's another simulation that he's showing, and this time it's the probability of detecting satellites, and he has a resolution of about 1 degree or so across the entire sky there. And again, if you can interpret that a little bit, it's also showing basically at twilight, at the beginning and ends of nights, you're going to be able to see more satellites. And this is from their observatory in Morocco. The next slide, please. Okay. And here he gives another, this time a histogram, and mostly it's of the brightnesses, the magnitudes that they are, they're projecting, and also they are confirming basically with what they observe. So, and so the number of satellites is on the y-axis here, and the magnitude, the brightness is on the x-axis here. And what we're trying to do is get better than 7th magnitude. So there are a fair amount of bright satellites there. And the number, if you can see on the x-axis, it does go above 1,000. And I think this is just for July 1st. They did this. Sorry, I'm a little parched here. Sorry. Now, from a totally different, next slide, sorry, totally different beast here. Something that I had never considered before is gamma ray observatory. Next slide, please. Sorry, thank you. Okay, so this is actually the gamma ray observatory that's Hess, and this is in Namibia, I think. And so Professor Michael Backus provided us with this information here. It's really interesting because, you know, if you do, they have a integration time of only 20 nanoseconds. And so if satellite comes by, it's basically going to be 1 pixel. It's going to be the same pixel no matter how many detectors you have around the area. Same pixels. You can take it out. But if over time you get tens of thousands of satellites up there, yeah, thank you, then you're going to have a problem. So let's get going here. Okay, I'm going to leave this next slide on radio astronomy to my colleague Federico, and he'll tell you all about that. And I'm going to keep on going. Now, there's just a couple of things I want to say about the mitigations from our community and then the mitigations from the satellite operators. And first and foremost, we've been studying it a lot, and I'll talk about the center in just a minute. So you can have simulations and modeling that we've been doing already at our center, and other people around the world have been doing, like you saw from Buskry. And this allows observations to be scheduled, so if you know when they're going to, the satellites are going overhead, and you can actually try to avoid them if possible. Another measurement includes simply closing the telescope dome, but that actually, you have to know exactly when they're going to be going overhead. And if you do, though, you can close the dome, but a lot of people don't have that capacity, to be honest with you. And so there's other things you can do here too. You can redo the observations, like some observatories will choose to do. And you can do some post-processing, but not a huge amount. So, if the trails are optically faint, you can do it. I should quantify that a little bit, and you can try to subtract them from the images. So let's go to the next slide. But again, all of this is going to take time and money, right? But the next slide, please. I can try to do it here. There you go. Okay. All right. So this is mitigations by the satellite companies, and there are some basic mitigations that they've already done, some like SpaceX has done, which I'll talk about in a second, that you could try convincing them that fewer satellites should be launched, but that's going to be kind of a futile thing to do. We have actually argued the point with SpaceX to lower their satellites in terms of altitude, which they have done actually. And we said this because they spend more time in the Earth's shadow and they wouldn't be actually seen visually, optically speaking. And they also are defocused if they're lower, believe it or not. You can use darker materials, which SpaceX has done, and they've used two different types. They paint the curved surfaces on the flat surface. They put sort of like a reflective mirror almost, and that reflects the light away from the Earth, basically. And they also use going over the terminator. They actually tilt their solar panels and the reflective parts of their satellite away from the Earth as well, so that it won't kind of get into the beam of the field of view of the telescopes, let's just say. So that's a couple of things that they have done. And sharing their data, that's another good thing. And attitude adjustments. So those are all these things that SpaceX we know has done, and they've also given their methodology to other companies to try to have other companies also take upon themselves to do these mitigation strategies. So let's go to the next slide, please. I'm going to go through this fast because I don't have too many minutes left, but the CPS is something you all should hopefully get involved in, if I can entice you guys. It is a burgeoning center. We've just started 2.5 years ago. We have an incredible crew of people, most of which do voluntary work, I have to say. We have areas in software and observations, which is called SAT Hub. We have a policy hub, which is obvious, both on international and national scales. We have a hub that works with industry and is amazing, has done amazing work in getting in contact and getting industry committed. And also a wonderful group called the Community Engagement Group, which gives a voice to people who are outside our field, basically. So communities like the indigenous communities, planetaria, even amateur astronomers, all sorts of communities are involved. And so let me go on to the next slide, please. I have a representation here. It's sort of like a model, I call it a model of cooperation with these 4 hubs involved. And this is what we do to achieve, try to achieve success, basically. Let me go to the next slide, please. I'll just talk very briefly. Okay. So for the SAT hub here, it's the Software Observations and Analysis Hub. And let's go to the next slide. I'm trying to go fast now. I'm so sorry. These are the various areas they've already accomplished. Oh, there's my, sorry. Yeah, I gotcha. Thank you. If I can go, just spend, Yes. Okay, so they've done various things here, and mostly it is in a wonderful program. They're now trying to model the brightness and the positions of various satellites and putting them in use so that we can have a program that any observatory around the world can use to try to avoid satellites, for instance, or especially over a certain brightness, which affects individual observatories. They also have a data repository, and that's a really big deal as well. If you want to learn more, I can tell you about that later too. Let's go to the next slide, please. The huge thing that happened the last couple of weeks, we won a big grant from NSF, yay, to do exactly this, the software and observations aspect of SatHub. So, and I can tell you more about that later too, if you'd like. So next slide, we want to talk about just the industry hub for just a moment. And they provide a safe zone for satellite companies to discuss mitigation techniques. And they have engaged both sides, I don't want to say sides, but both cultures, the astronomers and the industry, in adopting, trying to come together in terms of adopting the tools they could use for mitigations. And they have a new program called Astronomer Guides. And if you would like to be paired as an astronomer guide with a company, come see me. We can do that. And so, the next slide. So I've already talked about this. Let's go. We can't even see the bottom. But anyways, go to the next slide, please. Yeah. So we have the Community Engagement Hub, and I mentioned them a little bit already. They actually serve as the bridge, I said, to other communities that are not necessarily part of our professional field or the satellite industry. And they've done this. Let's go to the very next slide. They've done the biggest thing they've done is this wonderful group of videos, 8 videos, very short, between 7 and 15 minutes, that talk to you about the challenges and the mitigation solutions. Next slide. I'm sorry if you can't hear me. Mitigation solutions that you could explain to industry, you could explain to the public, you could explain to other astronomers. It's very good. You can find that on our cps.iau.org website. And this, our last group is the policy group. Next slide. I'm sorry, I'm not very clear, I guess. We have, and this is an amazing group, so well organized, 10 different work packages. It's amazing. And they have everything from a sort of a policy paper they just finished that you can find on our desk downstairs if you'd like to see in the exhibit hall. And as well as a beautiful brochure you might find down there about CPS. And they make it a point to study space policy, to talk about national regulations and guidelines and frameworks. They've gone to the UN and all sorts of things that we've done to accomplish the goal of getting sort of policy out there in terms of satellite constellations. But let me show you the next slide. And this is some of their accomplishments you can see. Next slide. There you go. Beautiful. Thank you. And I'd say one of the coolest things has been giving advice in terms of what we could do in terms of the UN Committee for the Peaceful Use of Outer Space. And I'm going to actually go to the very next slide, please. Do you want me to do it? Oh, there you go. Okay. Yeah. This has been a huge accomplishment I want to brag about because it took about 4 or 5 years to establish the fact that astronomy is a space activity at the UN. And this is the Committee for the Peaceful Use of Outer Space. And they have another group under that called the Science and Technology Subcommittee. And it's in that group now that we have a 5-year agenda item that's dedicated to dark and quiet skies in relationship to satellite constellations. This is a huge accomplishment. And I know that Federico is going to be talking more about the group of friends, which is behind all this and helping make this happen. So he'll tell you more about that. So just to mention, if you want any more information, let's go to the next slide. This is a place you have to go. Take a picture because you can find out about what our community is doing at large and what the CPS has been doing. We just had an incredible symposium last fall, an IAU symposium. And then the next slide, please. If you want to join us this week, please, 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 we have little handouts here for you that James will help pass out now if you'd like. And we have handouts on both our working group meetings. One is actually the CPS. The center is tomorrow all day. And then on the 15th, we have one on ground-based light pollution. And the last slide, I think. Oops. Oh, please, if you want to pass it out, yeah. Oh, sorry. We're going to have meetings in the future. Oh, the previous slide, sorry. We have meetings in the future, one in 2025, probably in Manchester, and maybe Federico could tell you more about that too, because that's his hometown. And then in 2026, possibly we'll have a Dark and Quiet Skies meeting in Chile. So please stay tuned. We're going to stay active. We are active. We want your involvement. It is very important. Okay, so please come see us and talk with us, and we look forward to talking with you. Thank you.
For this really nice talk. And, we now have another invited speaker, Ramatolu from South Africa, and he will speak about dark sky protection in South Africa. Go ahead, Ramatolu.
Okay, I would also want to thank the organizers for giving me an opportunity to talk about dark sky protection at South African Astronomical Observatory. Okay. Next slide. Next. Yeah, so I'll just briefly give you an introduction about the SAAO and its history. Next. And I'll talk about the legislation that we use to protect the astronomy facilities in South Africa, as well as related regulations. And I'll go into current status of what's going on at the observatory now. Next. And I'll talk about challenges that we have. We're trying to do all of this. Next. And next. So I think basically the South African Astronomical Observatory is one of the oldest observatories on the African continent. As you already had this morning. So our headquarters are here in Cape Town. And the telescopes that we have are in Sutherland. And the telescopes you see here were the first ones. Next. Were the first ones that, next. The first one that were, oh, okay. Hello. Okay, well, the first telescopes that went to Sutherland in 1972, when the observatory was formed from what was called Royal Observatory in Cape Town, where you see these buildings now, where they still house astronomers that work at SAAO, and the telescopes moved from Cape Town and Johannesburg to Sutherland. Next. And so this is Sutherland currently, and you have already heard about all of these telescopes, but I will be mostly talking about this little thing here called ASPONS. This is the all-sky monitor that actually we use to monitor light pollution at sky brightness. And it's used in conjunction with the regulations that we have basically to protect the night sky at the observatory. Next. Next. Okay. Next. Okay, in fact, before I go into this ones, as far as the telescopes are concerned, I think it's important to tell you that the telescopes we have, let's say the 1.9 and 1 meter telescopes that we talked about earlier this morning, they are basically available for anyone around the world. Whoever would like to apply for time, you are free to do that, and your project will be looked at, and if it's scientifically good enough to be offered time. It can be offered time. We can be able to do observations now remotely. And on one of the telescopes, you can even do it robotically. So the main legislations that we are using is called the Geographic Advantage Act of 2007. So this is the main legislation that we use to protect astronomy and related scientific endeavors in South Africa. Next. And out of that, there are related regulations. One is called the Regulation on the Protection of the Southern Central Astronomy Advantage Area. Next. And the other one is the Declaration to Prohibit Certain Mining Activities within Southern Central Astronomy Advantage Area. And this were sort of enacted in 2019 under notice 805 and 06. And okay, next. Next. So basically the act itself is basically empowers the Minister of Science and Innovation to declare protected areas around strategic astronomy sites or what we call astronomy advantage areas. Next. And it covers both radio and optical astronomy. Next. And it also makes declaration for the establishment of what is called Astronomy Management Authority, which has already been done. So we have Astronomy Management Authority within the Department of Science and Innovation, and that entity is the one that we are working with at SAAO to try and make sure that the regulations we have are not actually infringed. Next. So the protection of these regulations has got 3 tiers, the core, the central, and the coordinated. So I'll be mostly talking about the central area because that's where there are issues, because the land around that is not necessarily owned by SAAO, whereas the core is owned by SAAO. The central, in this case, is about 75-kilometer radius from the Southern African Large Telescope in the Northern Cape. Next. So this is the Central Astronomy Advantage Area. So here is in the Northern Cape. Here, the gray, the shaded area is in the Western Cape. So the protected areas are around here. Next. 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 So the regulations actually covers things like prescribed conditions for lighting activities within the Southern Central Astronomy Advantage Area. Next. And activities creating air pollution and regulations on wind turbines within the Southern Central Astronomy Advantage Area. This only covers the large wind turbines. So basically, and even within 20 kilometers radius of the observatory, we don't allow any wind farms at all. Next. And it has some annexures A, which just gives sort of the details of the moonless night sky brightness that should not be exceeded. Next. And another annex, which I'm not going to go into, so more about the dust levels and stuff like that. Okay, next. So this appears in Annex A. So these are what we call the natural levels of the night sky brightness at Sutherland, and the extinction values. And these numbers are not supposed to be exceeded by any outdoor lighting around Sutherland. Next. Next. So I mentioned the declaration to prohibit certain mining activities. So activities that are prohibited under this declaration include so for mining, next, and hydraulic fracturing. Next. Okay, currently there are things that are going on that we are dealing with in Sutherland. Like there's this construction of massive number of wind farms around Sutherland, but most of this we had sort of consultations with them as well with South African Civil Aviation, which basically requires them to have lights, but sort of have some mitigation measures. Next. There are other issues like prospecting applications that Astronomy Management Authority and SAAO are actually dealing with, which really is just a nightmare at the moment. And some outdoor lighting issues in the Sutherland town, which is just 15 kilometers away from us. Next. But I think the good news is that the moonless night sky brightness levels at SAAO are still close to what the natural dark sky brightness levels quoted in the regulations look like. Next. Okay, this is sort of a light curve taken with the little instruments that I showed you earlier. So they take like within every 5 minutes, they go through BVRI filters, taking measurements of the night sky brightness every night between twilights. So this is the light curve, but the whole light curve basically, including the moon times in 2024. Next. And this is the same light curve with we're removing the data that's affected by the moon. Next. And so actually that's zenith, so pointing straight up. And this is the same similar light curves in B, V, R, and I. So this are magnitude per arcsecond squared for this year. And you can actually see that there's not much difference, but okay. So these are, you can actually see the averages. And this ones actually include so basically the data that's not clear skies has been subtracted as well. So these are clear nights. Next. Same thing for pointing at different directions. So this is north, that's east, south, and west. And I think looking at this, you can actually see that, whatever you see here that may actually look like some issues, it does not necessarily appear to be coming from the ground, because if it was, I would expect that it will be only one direction that's affected. Next. So what I showed you now, so this is the results of so the average brightness per year at the observatory since 2016, and you can see that the numbers do not actually change that much. So we don't necessarily think that there are serious issues as far as light pollution is concerned at the observatory at the moment. Next. So this is the same for pointing at different directions, and you can see that the numbers in V are exactly the same for both the mean and the median. So yeah, looks good. Next, and exactly the same as what we quoted in the regulations over time. So, next. Okay, the challenges that we have is, I mentioned that we have had consultation when the wind farms were coming up in Sutherland. The South African Civil Aviation Authority had agreed that they will have parallel regulations governing the lighting on and off on the wind farms.
but it looks like now they are sort of they're no longer interested in doing that. I mean, there has been lots of changes within the Civil Aviation Authority institution. So this is really is a serious issue because, okay, thanks. A lot of the agreement with the wind farms was based on the premises that the lighting on those wind farms will only happen when there are aircraft passing above within the vicinity of those wind farms. So if we don't necessarily win this case with the Civil Aviation Authority, then we may have issues. Next. And then, and also there are some issues with, so basically Astronomy Management Authority is within the Department of Science and Innovation. So basically we do work well with this entity, but one of the issues is that they work with the legal team from the Department of Science and Innovation, and sometimes there's sort of different interpretations of the regulations, and so it looks like sometimes it will be very, very difficult for the legal team to actually work with us or agree with us if there are some issues that they may end up actually them having to represent us, or maybe even in court. Next. 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 Yeah, okay. Yeah, I think one of the other issues with a really serious challenge is that the protection regulations that I mentioned and the declaration to prohibit certain mining activities in the Southern Central Astronomy Advantage area, they do not mention prospecting. They only mention mining. And there are companies that are taking advantage of that, and they would say that they're doing prospecting instead of mining, and then they apply to go into those areas that where mining is prohibited. Next. And this is an example of one of those. Sorry, the observatory is there, and this company has got licensing to do prospecting there, which is right in our neighborhood. But this is done by the Department of Mineral Resources in South Africa. So there's sort of some issues between this government department and Department of Science and Innovation where astronomy management sits. So that's another challenge. Next. Next. Okay, I think that's close to where I would end. And I think the lessons that should be learned here is that we probably need education of the communities and stakeholders around the observatories regarding light pollution mitigations and benefits of keeping our night skies dark for science and humanity, and better communication in our case between government departments should really be prioritized to make sure that there's not really, they're not impacting each other negatively. And one of the things that I used to think that is really necessary for this kind of regulations and protection of the night sky is actually voluntary compliance with whatever regulations we have, but it looks more and more difficult with some of institutions. So I'm actually glad that we have these regulations and prohibitions, even though there are challenges. But I think that it's still better than to rely solely on voluntary compliance. Thank you.
I will quickly go to Federico Di Berno. It's from SKA Observatory 2. Okay. Perfect. Thank you. All right, great. First of all, can I confirm this thing works or not? This. No, perfect. So I don't have it. I'll just say next slide. All right, good. So while the slides are coming, first of all, thank you very much for staying until the end. That's great. And to explain that you're wondering maybe right now what the radio guy is doing up there. You maybe think of radio astronomy as light waves in a very, 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 very low frequency. And we fit, right, in this discussion. So, all right, I'm Federico Di Bruno from the SKA Observatory. We are a radio observatory. And hopefully I can tell you a little bit about what we do and what's the situation with large constellations and radio astronomy. Connie was talking a little bit about that. So let's go. Next slide, please. Just a little bit about the SKA. One back. Thanks. SKA Observatory. We are an international intergovernmental organization. We have 3 sites and 1 observatory. We have our headquarters in the UK, and we are building 2 of the largest radio telescopes in the world in South Africa and Australia. We have 10 member states, as you can see the flag there with the asterisks, 6 observer states, and 8 African partner states, where we hope that someday the SKA can expand into the African continent. Next slide, please. These are some pictures of the SKA MID in South Africa. In South Africa, we are expecting to have 197 fully steered 50-meter dishes, including the existing 64 Mercat dishes. Our frequency range will cover from 350 megahertz up to 15.4 gigahertz, and we will have a maximum baseline of 150 kilometers. Next slide. In Australia, we will have the SKA low, or low frequency one, where we will have in the order of 131,000 antennas grouped in stations of 512. And it's a very impressive thing. So you have on the right, that's an artist's impression of the SKA low. And surprisingly, it's starting to look like that. So you'll see some pictures next. The frequency range of SKA low, of course, is very low frequency, 50 megahertz up to 350 megahertz. And we have a maximum baseline of 74 kilometers. Next slide, please. Yeah, and then some pictures of actual construction, right? The first thing was an image. Now these are real pictures of the site. This is one of the clusters in SKA low. And you can see 4 of those clusters, which have a different bright gleam to them. And those are the ones that are populated with antennas. As you see here, these are 256 antennas individually sampled. So the amount of data that this thing produces is insane. Next, please. Text. So this is some pictures of the construction in MID. So this is the South African site. This is what we call the big lift, where we lift the reflector of one of the 50-meter antennas. And you see that down there in the picture, the Mercat telescope and the big lift there on the left. It has, of course, its very big challenges to build the telescope in the same site where the telescope is operating. We can talk about that if anyone is interested. I'm not going to go into the details, but we can discuss that about the interference that our construction produces and so on. Next slide, please. And last thing about the SKO is that we have our 2 sites in very protected remote areas. So both our sites are protected by radio quiet zones. And what a radio quiet zone basically means, it doesn't really mean that nothing can emit in there, right? That's a little bit of a misconception that comes from the name. A radio quiet zone is a geographical area where the use of the radio spectrum is specially managed, right? So we have special protections, as Ramato was talking about before. There are lots of protections that have a lot of processes to enable or to license transmitters in them. So this is a very protected areas. And as you can see, are huge areas, right? So these areas also include towns in there. So it's a challenging process to try to keep the sites as quiet as possible in the radio regime. Next slide, please. Okay, so that's all I'm going to say about the SKO specifically. But if you're interested, please have a look on Friday 9th. We will have a full day of SKO. And
you can see the information on this particular event is on the scientific events. I think it's in the program website of the IAU GA. Next slide, please. And the interesting thing is that all our speakers are women. So if you want to know more about the SKA, you can find out from our wonderful female colleagues in the day of the Women's Day on 9th. Next slide, please. Right, so Connie made a great introduction to this, so I don't have to delve a lot on this slide, but basically we have facing new threats from the sky, right? The sky is from space. Space is getting crowded and crowded. And what's happening is that the likelihood of having a satellite in front of our beam is increasing, right? We cannot say that this is a new thing, right? Radio astronomy has been dealing with satellites for forever, but the situation is changing a lot, right? And these satellites are producing radio and light pollution, as Connie was saying before, and radio quiet zones do not formally apply to satellites, right? Radio quiet zones are very effective on the ground, right? But when things are in space and we see them in the sky, it's much more difficult to control them through the radio quiet zone regulations. Next slide, please. Connie explained this very well, so I won't go in detail. Also, I don't know as much as she does. So let's go to the next slide, please. And yeah, a little bit about the radio impact. So if you think that the radio telescope is just one antenna or a collection of many, many big antennas trying to listen to these very faint electromagnetic signals coming from stars or galaxies or whatever. And you have some satellites going around, next slide, that can produce very strong intentional emissions, so downlinks, right? The satellites, of course, need to connect to the Earth. They want to provide internet connectivity or something. So we got very, very strong signals coming into the ground. Next slide. And we also have other effects, such as unintentional electromagnetic emission, right, or UEMR. And this thing is not so strong in communication terms, right? So if you compare the unintentional emissions of a satellite with the intentional emissions, these are way, way, way weaker than the other ones. But in astronomical terms, they are still very, very strong. Next slide, please. So a little bit on the two of them. So the intentional downlinks, these are very strong signals, and they can saturate receivers. They can interfere with allocated radio astronomy bands, so the bands that are reserved, the pieces of the spectrum that are reserved for radio astronomy. So emissions in there can interfere with these bands. They can block big parts of the radio spectrum, right? There's a thing that we need to realize, that the radio spectrum is divided in bands, and each band is assigned to different users. So sometimes it can happen that a big portion of the spectrum is just used by satellites and we cannot access it. So the frequencies normally for intentional downlinks are about 2 gigahertz, 1-ish now, depending on what thing we're thinking about. And the unintentional emissions, the thing they have is that they are normally not constrained in frequency, right? If you think on intentional downlinks, you can find exactly the frequencies that some satellites are transmitting, but that doesn't happen for unintentional emissions because they're unintentional, right? So they can be generated in any frequency in principle. And they are quite intense if you think on astronomy terms, so in the order of 1 to hundreds of Janskys. They are not regulated normally, so there's no regulation, whereas for intentional downlinks, there is a regulation. For unintentional emissions, there's no regulation in place. And it normally happens in lower frequencies, so under 1 gigahertz. Next slide, please. All right, so what are we doing about this? Connie mentioned a little bit of this. So some countries are trying to put some conditions in the licensings of these constellations. So when a constellation wants to offer the service in the country, some countries are starting to put some conditions to protect astronomy. Not all of them, I would say the least of them, but that's starting to happen. We are working at the ITU, the International Astronomical Union. I'll talk about that later. And we are working in the UN COPOST, as Connie also mentioned. And we are, of course, working a lot in the IAU CPS. Luckily, Connie mentioned everything, so I'm not going to go into that. And we at the SKO and several other observatories were working on software mitigation measures, right? We need to put software in place to try to deal with this. Next slide. Thanks. So on the ITU is the International Telecommunication Union. It's a UN agency that regulates the radio spectrum, right? So they define, all the countries really define how to use all the different frequencies in the radio spectrum. And in there, we are a sector member of the ITU, so we go there and we advocate trying to protect astronomy. And we have a very, very good cooperation with SAAO, with the AMA that Ramatolo was talking about, and with ICASA, who is the national regulator in South Africa. And we collaborate very well with them, so we have obtained, let's say, I don't know if it's the best word, but we got an agenda item for the World Radio Communication Conference. This is the conference that every 4 years revises the international treaty that defines the use of the radio spectrum. And so that's where I was talking about that some emissions have a very well-established regulatory framework. Right? So every 4 years, there's a revision. And right now for 2027, we are working, this was established in 2023, right? So in 2023, we got this agenda item, and now we need to work until 2027 to argue that we can protect radio quiet zones from satellite constellations. And this was mainly possible thanks to the African continent. Right? I think that's a very, very important thing to remark. We got a lot of support by the African Telecommunication Union and spearheaded by South Africa. So the support from them was instrumental to get this agenda item in place. Having the agenda item in place doesn't mean that we will eventually get some positive result, but it already means a lot, right? So we need to keep working on that. And we are also working on a report on UEMR and intentional emissions. We are working on that at the Working Party 7D in the ITU. And it's also a very important work because, as I was saying, unintentional emissions are not regulated. So if you go into the ITU and you argue that these emissions, this radio noise from satellites is producing interference, the ITU will say, well, okay. So this is what we are working on right now in Working Party 7D, trying to raise awareness and eventually leading into regulations. But we need more support on this one. Next slide. Okay, that's good. Connie did mention a little bit of this, so good that you all know what the UN COPWAS is. And she also mentioned what there's an agenda item that will last for 5 years in the Scientific and Technical Subcommittee of COPWAS. This is a very, very important thing, and this is my personal opinion in here. So it's not so much for what the regulations will come from COPWAS, because there won't be any international regulation from COPWAS. It's likely that at some point there might be guidelines that come from COPWAS, international guidelines on how to protect dark and quiet skies. But what is very important from this work is that anyone in a country can go to the regulator in the country and argue that there is a lot of discussion in this very high-level committee at the UN, so you can get a lot of traction at the national level, right? I think this is one of the most powerful things about having an agenda item in COPWAS. And Connie did mention that there's a group of friends for dark and quiet skies, so this is an informal group within COPWAS. And the interesting thing about this informal group is that experts from the different countries can participate in this group, right? So you, as astronomy experts, can get in touch with your regulators or the mission that goes to COPWAS, and you can contact them and tell them and say to them, like, I'm interested in working in this group of friends, and we are working right now in creating some focus groups that will work on particular technical questions, and that is something that you guys have something to add to it, right? So you can definitely work on this. Happy to talk about more on this offline if you wish. Next slide, please. So I think this is the last one, and about the opportunities for Africa, what Africa can do. I think one of the most important ones is these questions about licenses for satellite constellations in the countries. While the idea of having international regulation is nice, and it would be very good if there were, the reality is that the power we are seeing from conditions or trying to get the operators to talk to astronomical observatories is this conditions for the licenses to operate in the country, right? So if there are these different operators that want to operate in the country, if you get your regulator to say, well, the condition is that you need to coordinate with my observatory in the country, this is what the US is doing, for example, it's very strong, right? Because if they don't talk to the observatory, they don't get the license. This is very important. Yeah, I'm almost done. And the leadership on the agenda item 1.16, in particularly for radio quiet zones, this is very important. And then we hope that the African continent and the South African regulator are still going to support us. As I said, this was instrumental in WRC 23 to get it. And as I was saying before, right, the participation in this group of friends, it's only up to you, right? It's quite informal to participate in this group. So the only thing you need to do is find out who are the people that go to COPWAS, and you can just contact them and say, I'm interested in participating in this, in helping you. This is what they really need. These are diplomats, so diplomats don't know much about the specific topic. So you can give support for the diplomats that work at COPWAS in the technical focus groups that we're creating there. And I think that would be it. Next slide, please. Yeah, thank you very much for your attention.
Federico, we are late. The opening ceremony will start soon. If you can have 2 or 3 questions about the anti-function. Is there any question? Otherwise, we have at the last session tomorrow, the discussion slot, and we can exchange about this topics. Yes.
Hi, thank you. James Lowenthal from the United States. I have a question for Ramotolo. Can you say a few words about what you think has been the most effective kind of messaging when you are trying to convince your national agencies to talk to each other? Is it mostly about money, the economic benefits of mining versus the economic benefits of astronomy, or is there some other value that is at play in the discussion?
Thank you. I mean, it's not really clear to me. As far as things like wind farms, for example, I mean, we definitely have issues with energy in the country. So we do see the need to have them within those areas, but actually just have mitigation measures to address things like light pollution from those kind of things. That's why we had all the sort of the consultation with the Civil Aviation Authority to so come up with options that can have the wind farms and us coexisting in those areas. As far as mining is concerned, like I said, that we actually have prohibited mining within that 75-kilometer radius. I mean, the difficult thing is that the Department of Mineral Resources, it's basically, for them to license mining, it's their KPIs. So basically, that's what they do. Every year they say, well, this is the number of licenses we have dished out. So which is right in conflict with what we are trying to do. But I mean, South Africa is quite a large country, and even the Northern Cape, where the astronomy advantage areas are, is the largest province land-wise in South Africa. So 75-kilometer radius is really a little, it's nothing. So they can actually do something else outside that area, which even though we may not necessarily like it when they're closer to us,
But you know, I don't think that's you know, we can do anything if they do something else outside the area that's protected. Thanks.
Can I ask?
Yes,
Okay.
yes, please.
Thank you, Professor. So, actually, I have a question regarding the results you actually showed. I've seen that you say that we reached to about 25 magnitude using your tool. Is it reasonable to 25 magnitude?
Yes.
Hmm? And I've seen that in all bands.
Yes, yes, in the
Okay.
No. It was
which
B-band.
which instrument you use for this value?
It was BVRI.
Yes.
Yeah. So which one you have issues with?
I think
The limit is
Yeah.
22. You
Okay.
said in the visual.
That's
Yes.
right. Yeah. Look. So this is what the instrument is actually. That's the measurements it's actually taking every night. So I personally don't necessarily care if the magnitudes are above, you know,
Yes.
So I don't know what that means.
Yes. I mean, yes.
Yeah.
I think they need the calibration. Yes.
Gaia can reach to 22 magnitude.
Yeah.
Gaia is telescope.
Yeah. No. But I think you have to understand this is magnitude per arc second squared. That's you know, if you remove everything. Yeah, that's surface brightness. So that's not what you're talking about.
Yes. I have the same question as you about the values.
Oh, you have the same issue as well.
Yes, as the limit of magnitude present in your slide is very high. I think the instrument need to be calibrated.
No, the limit I use, that's that's coming out of the instrument. You know, but anyway, I just don't think, I mean, I don't think it's I think the main issue is if the brightness goes below or higher, in the sense that the numbers comes down, so you get, say, 20 in V, which would mean that there's some issues with light pollution. But I don't necessarily think that the instrument is actually calibrated, you know, to a certain maximum number. But there are other issues. That's why a lot of things that I subtracted lots of things, like, you know, data that's affected by weather, data that are affected by moon and stuff like that. But, you know, some of those subtractions may not necessarily be, you know, we can find anyway. But yeah, I get what you're saying, but I don't necessarily think. Yeah.
Thank
Okay.
you. Is there any other question? Warren is still, I see, with us. If yes, David. Yes.
May I ask Warren a question, please? Warren, you started saying that we can make science goals or science book just after having the idea of constructing a new telescope. Does it depend on the characteristic of the site itself to have science goals or science book? I mean, the probabilities of the characteristic of the site itself can affect the science goals or science book from the beginning?
Can you hear me?
Yeah.
Yeah, they can. All of these things are interrelated. So having an idea of potential site characteristics that you might look for. You know, everyone wants, you know, lots of clear nights and a good turbulence characteristics and things like that. So you can pick any kind of decent site at first, or that can be your baseline, and perhaps you as you get a better understanding of the science and the design, as the project starts to mature, you may revise the requirements for you may change the idea for the site that you want. You probably have a few sites at first, and you identify 2 or 3 of your favorite sites out of that group. So I think the answer to your question is it's everything is somewhat related, and you can't just focus on one thing. You have to try to balance all of these things all at the same time as best you can as you develop the idea for the project.
Thank you.
Okay, thank you.
Question?
Hi, Warren. Just regarding science books and science drivers for projects, and like many years before the actual construction of the telescope is completed, just a sort of word of caution that I know we have to write science drivers and science books, but to some degree, they become out of date. Sometimes at the time the facility comes on air, a lot of those science drivers are no longer the top of the heap because of what's happened, because our field is so dynamic and discoveries happen before that. So I think I don't know how that's handled by funding agencies when they look at science cases and then they look at what the facility has actually delivered, but they need to be aware that there's a fair degree of crystal ball gazing that happens when you're writing science drivers, and you can't really predict what discoveries are going to happen. But just to say that it's not set in stone, that it's and obviously your science drivers have evolved for TMT, as you had on your slide with the inputs from JWST. Eventually you've got to draw a line in the sand and say that's it, but it's not the end of it.
Thanks, David. You're right that science does move on. One of the main roles, I think, of a science book and having lots of science cases to think about the observing capabilities is to make sure you have a flexible set of observing capabilities that at some point you can say, look, they are in line with the latest science. One thing we've seen in TMT is even as the science has moved on, the actual observing requirements, the observing capabilities that you need in order to answer the next set of questions, it basically stays the same, because until you build a 30-meter telescope, you don't have the diffraction limit of a 30-meter telescope, and so there is even you just do not have the observing capabilities until you build it. So it means that once you do get a pretty good set of observing capabilities defined, that at least for us, what we've seen is that it's remained quite robust over time, and it's just the details of the science have changed, but you still 20 years ago we wanted to look at high redshift small galaxies, and still today we want to look at high redshift small galaxies, but it's only really the details of the science which have changed, but the capabilities have been pretty steadfast.
Thank you. Thank you all, and meet you tomorrow for the next 3 sessions of this focus meeting. And Atlas, yes, Atlas session, we have about 20 minutes for discussion. 14 minutes, okay. So we have enough time to exchange about
the topics of this focus meeting. Thank you.